So I'm Ross Drummond. I'm a lecturer at the University of Sheffield now, and this is a webinar on the control for clean energy. So this is part of this ACE network, which I'll get into in some more, and hopefully in the next 3 hours you'll learn about research happening in the UK control community on kind of control of batteries and control power systems and even of ventilation systems as well. So this webinar is as part of some activities involved in this ACE network. So I'm going to give you a quick 10-minute sort of spiel about what this network is and why it's here. So it's the Automatic Control Network and started in January 2024, it's funded by the EPSRC for 3 years. And its goal is to basically create interdisciplinarity within the control community, kind of drive forward control research in the UK. I mean, in essence, we're not friendly enough. We need to chat to each other and support each other. And these networks are trying to support that here. So looking forward, this is an interesting time for control. And how do we as a community kind of embrace those challenges and even sort of shape them? So that's what ACE, this network, is all about. So so in terms of the motivation for why this network exists, well, there's some kind of compelling reasons why control needs a network to try and bring us forward, really. So there's a strong control community in the UK. Some of the really cool innovations happened here, but it's maybe less visible and less influential than what we'd want it to be. So control is a hidden technology. It's just maybe in the UK, it's really, really hidden. So the idea of these sort of networks is to try and bring it forward and try and promote it as much as possible. Then as well as that, so control continues to make a huge sort of progress, and it's really kind of all new technologies, and even the AI and machine learning, they're all really using control. So how do we try and connect to those technologies, those applications, those areas, those fields, in a way which we can really make a contribution to, and which we can learn from them as well. So we have to adapt with this new world and sort of solve some new interesting problems. So how do we do that? And I think one way is by just talking to each other and talking to other communities, and that's what a network does, really. So another reason why we need a network, other disciplines have really sort of grown, especially in participation and funding, really. So if you look at things like fluids and it look like machine learning, those are really grown, whereas control has really sort of stagnated or even reduced the amount of funding available. So can we try and promote the use of control to try and get a larger pot and try and support more fundamental research, really? I mean, just emphasizing that. So in this bullet point here, I joined Sheffield in the Department of Automatic Control and System Engineering. After I joined, they somehow wanted to close that. I'm not sure if the two are linked, but so I'm now part of the School of Electrical and Electronic Engineering. So kind of control-focused departments, control-focused undergraduate courses are kind of reducing in the UK. So we have to kind of band together to try and shape the new generation of what control is going to be in the future. So how do we, hopefully with these networks, and especially with these early career researcher networks, which Philby was kind of leading, we can kind of try and promote the next future leaders in control. So what are the next generation of control engineers going to look like in the UK? Hopefully we can do that. So again, a bit more about ACE. So it's connected to UCAC, which is the UK Automatic Control Council. So that is the UCAC is the kind of the advisory or I guess, sort of semi-governing board, the kind of elders of control in the UK. And ACE is a network which is helping to promote some of those activities, but also doing its own thing. So ACE has 200+ members from various UK universities, it has industrial partners, and it's also connected to various of the UK catapults. It also has, by the end of the funding, hopefully what ACE has achieved is on this right-hand side here. So hopefully we have a more interdisciplinary research community. So hopefully we all know what each other is doing in control in the UK. We all have an understanding of that, and we're trying to be more supportive and try and support each other to try and get those big grants, try and promote control as a as a technology which needs to be celebrated and pushed forward in the UK. As part of that, ACE hopes to develop some sort of vision, so some long-term goals of how control is going to be shaped in the future. And also, so as well as those visions, so those are research visions, also technology, a virtual center of excellence, and increasing grant capture. So really trying to, through collaboration, try and promote control. There are several activities. So there are several roadmap consultation, which are going to happen fairly soon to generate some white papers. There's various industrial workshops, there's some sandpit events, and even these grand challenge research council meetings, which are happening. But really the main event in the calendar for this network is this network forum, which is going to happen on the 24th of March, 2025. So that's going to be at St Hugh's in Oxford. It's really the first kind of major gathering of the control community as part of this ACE network in the UK. So there's going to be lots of sandpits and lots of ideas really flowing around to try and drive forward control. On the 25th, so on the same day, or on the following day, as well as St Hugh's, there's going to be Duncan Fest, which is, I'm very biased here, but so Duncan Fest is celebrating the retirement of Stephen Duncan, who is a professor, I think, at University of Oxford in control. He was my supervisor for 10 years, so I'm very biased here, but it's basically going to be fun. It's going to be a jolly, if you know Steve, he's very nice, very friendly, and loves control. And that's going to be the basic tenet of what that day is going to be. So come along to Duncan Fest. So ACE in itself is kind of split in 4 quadrants, really. And these are called grand challenges. So there's AI and data, which is all, AI and data. There's feature mobility, so that's things like electric vehicles, smart cities. There's aging society, which is human-machine control systems and biological systems and control for society, really. And then there's a final one, clean growth, which is what today is all about. And then around this, there is this early career research committee, again led by Phil, which is really starting to really be quite vibrant and trying to kickstart events. So there's been webinars, it's been the start of it on these 3 here, so on AI and data, feature mobility, and aging society. And we're going to be the final one today on clean growth. The clean growth itself, it's kind of led by Manchester contingent of Alessandra Parisio and Konstantinos Fedoropoulos. And its 4 main themes are around energy, manufacturing, food, and climate change. So big meaty topics there for control to engage with and try and develop new ideas with. So this webinar, the kind of focus is on the top bullet point there. So it's control and optimization of energy systems, really. So we hope later on we've got scope to do manufacturing. We can do the control of lettuces, for instance. So I think Fulvius has some stuff on that recently, and even climate change. But today we're going to be focusing on energy. And we have this array of speakers here. So the idea is it's people kind of fairly early career. So people who are still passionate about research and what they're doing. So we have early career researchers working on control, but also a bit of power, a bit of energy, a bit of batteries. So we've got Francesca Boem from UCL, and then we've got Pablo from Sheffield as well. So these are 2 talks on microgrids, really, as far as I'm aware. Then we're going to have Carolanne, who's going to tell us how we should control some ventilation systems. We then got the 3 battery postdocs from the Dave Howie's lab, the Battery Intelligence Lab, of Noel, Brady, and Volkan, and they're going to tell us how to control and parameterize our battery models. And then we've got Yuanbo Nie as well, who's also from Sheffield and is just over there. He's going to tell us about his battery zoo, which is all quite exciting, a zoo of battery models. And then finally, we're going to have, hopefully, Adrien Bizeray, who's one of the founders of BrillPower, which is a really cool battery startup. So they do the decentralized control of large battery systems. So we're going to hear from him about how to commercialize some of this technology. So the schedule is kind of roughly into 2 sessions. So we're going to have a kind of control of power systems. So anything which kind of fairly large scale controlling of power, really. Francesca's going to lead us there on her work on microgrids. For Carolanne's going to talk about air quality, and Pablo's going to be back to plug and play control in microgrids. We're then going to have a sort of short panel discussion and a break, hopefully, which hopefully will be working. I've never done a panel discussion before, but we'll work with that. And then we're going to, the second session is going to be about batteries. No, so I think I've lost my screen. So second session is about batteries. So we're going to have Volkan talking about how to make money from batteries. So pure capitalism of batteries. So Volkan's going to tell us how to optimize and control that. We're then going to have two talks from this PyBop toolbox, which has emerged from fairly recently from the Dave Howie's lab. And so Brady and Noel have really driven that forward. So that'd be really cool. And then finally, we're going to have Yuanbo talking about the battery zoo, and Adrien's going to tell us about BrillPower and how that commercialization journey started. So we're a bit behind time already, but with that, I'm going to start passing over to Francesca, if that's okay.
Yeah. Good afternoon, everyone. And first of all, thank you for the invitation. I will share my screen. And yeah, hopefully you are seeing my...
Yeah, perfect.
Okay, let's see if I can... Okay, perfect. Now I can see it as well. Yeah. Okay, so today I'm going to give you a brief, let's say, overview of my work around the topic of microgrids, and specifically on the aspects of safety and reliability and resilience of microgrids. So yeah, as Ross said, I'm associate professor in control systems at UCL in the Tripoli department. So as most of you probably know, since you're here, what a microgrid is. So a cluster of loads, generation and storage units that as control engineers, we want to coordinate and operate to reliably supply electricity. And it is usually possibly connected to the grid. My focus in the past years has been specifically on the aspects of how to consider the threats that we might have to the efficiency, safety, and reliability of microgrids. And these threats come from a variety of sources, from general uncertainty, so modeling, uncertainty in the profiles, potential external disturbances, but also the uncertainty that comes from the use of AI and machine learning and their possibly unpredictability or difficulty to interpret. Then we have, of course, also the problem that these systems, as all the systems, can be affected by faults in the systems, in parts of the equipment, or in the sensors. These systems are also, since we want coordination, there is communication networks, and these ones as well could be affected by problems, delays, non-reliability of the communication, and the potential, let's say, vulnerabilities due to cyber and cyber physical attacks. So attacks that specifically target the physical systems. Moreover, we can add the fact that microgrids are growing. We can think about networked microgrids, and for the problem of privacy concerns that could, let's say, undermine our possibility to increase efficiency in the control of these complex systems, as well as the interconnection that could add to the uncertainty that we might have in the model and in the other variables and parameters of the system. So I'm really just touching based on the fact that in the past I've worked quite a lot also at the secondary layer control. As you know, microgrids have a hierarchical control structure. In the secondary control layer, I've been working a lot on aspects related to cyber-physical attacks, and now we can detect these attacks using the control perspective. So knowing about the physical dynamics and how this knowledge of the physical information can help us in promoting the security of the system, especially when we have communication in distributed control architectures. So detection of these attacks and then aspects of resilience. How can we make the control architectures more resilient and robust to the possible presence of these attacks? However, today I would like to focus more on the research that I've done in the tertiary control layer, and therefore I will be talking about energy management. In this layer, the main aspects that I've considered are the problems related to uncertainty, fault resilience, and privacy. And more specifically today, I will focus on the first two aspects. So how can we deal with the uncertainty that possibly comes from external disturbances and the uncertainty that we have in the model of the microgrid, and how to deal on the possible occurrence of faults when we want to schedule the energy management in microgrids. So that said, what is energy management? Energy management system is the controller that computes the power flows in order to optimize energy production and storage, so to deliver power to the loads, as well as minimize the operational cost of the microgrid. One of the main challenges in this is the fact that we have uncertainty, mainly in the profiles of the power production due to renewable generation, for example, the electricity price, and the uncertain demand. So what is the standard approach that we can find in the literature? We usually have, we design offline a predictor for these uncertain profiles, and then we use online the forecasts of coming from this predictor to compute a scheduling. This can be done, for example, through an MPC controller, as we can find proposed by our community. However, what are the problems there? The problems are that we are not considering in this approach the changes that can happen in the environment. We could have installation of new equipment, so changes in the load demand, as well as faults in the model, in the storage, or shocks in the market. That could affect the prices of the electricity and change the model that we are using for the prediction. Moreover, we could have changes in the model, in the dynamic model that we can use, that we are using in the MPC. So losses in the batteries, aging, or faults as well in the storage system. So what can we do? The idea has been to propose a novel learning-based MPC architecture that allows to, I don't know if you can see my the arrow on my mouse, but anyway, what we are doing is to embed the MPC controller as the final layer of a neural network through a differentiable optimization layer, and to target to train our neural network directly targeting the control cost. This is called task-based learning or performance-based learning, and which means that instead of minimizing the error of the profiles, so the mean square error of the profiles prediction, what we do, we train the entire network in order to minimize the cost of the MPC. This allows implicitly to make the the network learn also external uncertainty that there could be in the model or things that we are not modeling at all. So not only the profiles. And we can simultaneously continue to guarantee constraint satisfaction due to the fact that we are considering it inside the neural network through the optimization layer. What are the challenges there is that, of course, we will need to compute the gradients through backpropagation in a suitable way, so to take into account of the cost of the controller, and we need real-time implementation. So what, in order to allow this real-time implementation, what we have come up with is a new online learning methodology where we allow the neural network to continue to train online as new data comes available from the microgrid. So as new, for example, demand or both the load demand and the generation data and new prices come available, we continue to update and to train the neural network, so to adapt the predictor as well as the controller through the changes that can happen in the system. We have also adapted to this online functioning some existing say tools that we have in machine learning, stochastic weight averaging and experience replay, that allows us to improve generalizability and adaptability to different systems, such as transfer learning capabilities. So now let's go back a moment to the microgrid model. So we are considering, I said, renewable generators, loads, and the dynamics is, in this case, mainly due to the model of the storage system. We consider a first order model, but of course we could also complicate this model depending on specific requirements. And we set some limits, some constraints on the power and the charge of the battery. The goal is, of course, to minimize the total energy cost. As said, we have our controller is therefore composed by 3 layers. The neural network, this learning-based controller, is composed by an LSTM layer, then followed by a dense layer that produces the prediction of the uncertain profiles for the generation, the load, and the prices, which then enters in the optimization layer of the neural network as a part of the cost function and of the constraints. We then train this neural network targeting the control cost function. Just to add, in the experimental setting, we have used profiles which come from real-world data and our data sets that are available online, as well as actual electricity prices that we got from online available resources. We compare different performance indices, both the total cost of the control and of the MPC, as well as the mean square error, in order to evaluate both performances in our controller. So first of all, we have done an experiment in order to see if this online learning actually allows to improve our capability of prediction. And what we found by comparing the online learning MPC with the same online learning MPC, but we stop updating the weights after 1 year of online training. And what we see is that the online learning capability actually gives an advantage in adapting to changes in the profiles. We can see in the pictures how the online learning can adapt to changes in the load. In this case, the addition of a new equipment. We can see how the online learning predictor can actually follow the changes of the ground truth after some time, while the non-adaptive predictor will not be able to adapt to these changes. Similarly for what happens then in the prices, and we can see this better performance. Then it's been very interesting to see how, if we train the neural network based on different losses, so the traditional mean square error of the prediction profiles, then the new task-based performance, which is the cost of the MPC, and the hybrid cost loss function that combines these two, we can see how the task-based approach can actually allows to achieve a better performance, even if the error in the prediction profiles is higher. Moreover, we have tried to add uncertainty in the model. So we give to the MPC a wrong battery model for the charging discharging rates. And what we notice is that the online learning MPC can actually learn implicitly the unknown model parameters and corrects the incorrect battery model. So we see how the task-based approach actually gives an advantage for energy management. Finally, a very interesting thing is that the online learning capability allows us to have great transfer learning great transfer learning capabilities. What does it mean? Not only we can move we can transfer the approach from one microgrid to another, but actually we have noticed that if we train the online learning controller on one microgrid and then we test it on a completely different microgrid, we can obtain much better results, meaning that the model is able to capture also some is able to capture unmodeled uncertainty, which does not come only from the profiles, but also can learn hidden, let's say, modeling features. Okay, that said, how can we use this logic when not only we have uncertainty, but also we want to be resilient to faults? Okay, and what does it mean being resilient to faults? So the main strategies that we can find in the literature are proactive scheduling, so ensure that the scheduling is actually ready to handle the fault before and gets ready for the fault before it occurs. And then we have the outage management strategy, which means after fault occurrence, how do we deal with the situation? Of course, having a good proactive scheduling makes the microgrid in a better position to manage the outage after the fault occurrence. So now I'm going to show you mainly how we focus on the proactive scheduling part, but we have works where we have also considered the outage management. In here, I will also just focus on blackouts. So we have the microgrid becomes disconnected from the grid, but we have also seen how this architecture can be extended to different types of faults, line faults and generation faults as well. So what is the approach in the literature? So the main approach is to allow the storage, the batteries to store more power in order to be ready to support the potential blackout and to be, let's say, to be able to sustain the demand for a certain period of time that here we call tau, for a certain number of time steps. What are the problems with this approach is that it is, of course, conservative, does not adapt to possible changes, does not consider the probability of a fault that could change over time, and does not consider the uncertainty that we have in the profiles, of course. So we thought, okay, we should take this into account with our approach that allows online learning. So the first idea, if we had just to use the standard logic, would be to use the approach that I've just presented you and to add, let's say, a constraint that says that the storage should be greater than let's call it a backup storage that we could, for example, define as the maximum load multiplied by the number of time steps that we want the system to be resilient for. However, this assumes that the fault could happen at each time step and does not consider the prediction uncertainty. So what if this maximum load is actually not realistic? So the idea has been to combine the online estimation, but also to quantify the uncertainty that we have in the learning-based predictions, as well as use a proactive scheduling that jointly considers the uncertainty of the load demand generation and the probability of the fault. So we would like to change the constraint where the stored energy, so the stored energy is greater than the load requirement, with the probabilistic MPC constraint, where we say that the probability that the stored energy is greater than the load requirement is actually greater than the probability of the fault. How do we implement this? So we have designed a methodology so that the neural network directly is able to quantify the expected value and the variance of the uncertainty of certain profiles, and this way can automatically quantify the uncertainty that we have in the predictions of the profiles. And this is done here by assuming that the profiles are uncorrelated and Gaussian, and by minimizing the negative log likelihood of the loss. So we are asking the network to learn these expected value and the variance of the profiles. We are also working at reducing and removing these assumptions. Then we need at this point to modify the chance constraint that we would like in order to make it deterministic for the implementation in real time. And what we use is to modify the chance constraint using the Cantalis inequality, and therefore we can exploit and reformulate the chance constraint in a deterministic way as the one that we have here at the end. I will not go into the details for the sake of time. So what we obtain is that we have the online learning algorithm that I show you again, and then we modify the optimizer so to take into account of the probability of the fault occurrence, as well as the uncertainty that we have in the predictions of the uncertain profiles. We have implemented this in the experimental results with the real data, similarly as what I showed you before. And what we see here is in blue the ground truth. In orange we have the predictions, and we can see these bands, these cubes around the prediction, which is the uncertainty. Of course, it can happen that the prediction is outside the bounds, but what we notice, since this is a probabilistic approach, but what we could see is that the chance of error respects is in line with the 68, 95, 99.7 rule, the Chebyshev rule, if we want. So this is the experimental results reflect the theoretical guarantees that we wanted to obtain. And then the interesting aspects that we see is that this online resilient stochastic energy management MPC allows to adapt to the different uncertainty in the profiles and to the different fault probability. And we can see that more energy is stored in moments of higher uncertainty in the profiles, as well as that more energy is stored when the fault has higher probability of happening. which is what actually we want in order to avoid too conservative results. Of course, we have a trade-off between the resilience and the economic performance, but this can be tweaked or can be set properly by the designer in order to the desired, let's say, level of resilience that we want. So just now concluding, I showed you how we can combine machine learning with the MPC in order to have enhanced performance and prediction capability while continuing to guarantee safety and operational constraints. The online learning approach allows us to adapt to changes in the environment and the use of a performance-based or task-based approach permits to adapt to changes or to unmodeled uncertainty in the dynamic system. The algorithm has good transfer learning capabilities. If you're interested, the simulation code is available in GitHub. And as I show you, this can be extended also to allow resilience in the microgrid energy management by taking into account of the uncertain profiles, the uncertainty of the profiles, as well as the probability of the fault. We are working at combining outage management with the scheduling, with the proactive scheduling, and interestingly, we will consider different types of uncertainty quantification in order to remove the assumptions that we have. So I will finish here, and thank you so much for your attention. Thank
you, Francesca. That was great. I have loads of questions that I could ask about robustness, but in the interest of time, could we maybe just go swiftly to Carolanne's talk? And if you have any questions, please feel free to reach out to Francesca. I'm just trying to hit this timeline. It's so if you have any questions, please reach out to Francesca. And next, can I get Carolanne?
Yes.
Hope that's okay, Francesca.
Can you hear me okay? And can you see my slides? All good?
All good.
Cool. Yeah, so I'll get started then. I guess it's a bit of a different talk in that I'm not going to be presenting any kind of results or any studies, but more introducing a problem which I think is interesting and I think the control community should be looking into. So I'm a lecturer in building physics, also at the University of Sheffield, but in the School of Mechanical, Aerospace and Civil Engineering. And to give you a bit of background, my research really focuses on fluid dynamics for the built environment, and I'm particularly interested in looking at the links between natural ventilation and indoor air quality. So to do that, part of my work has been to use CFD to kind of model idealized environments and to look at the effects of the ventilation design, how that could have an effect on the air quality and how air is distributed in the room. And then that's kind of on the more idealized, perfect side. And then I've also done stuff in more messy environments, particularly in classrooms, using kind of low-cost monitors to look at the air quality over quite long periods of time, trying to identify what are the big factors that impact air quality and what could be done to kind of help mitigate that. The reason I'm here today in this specific seminar is buildings consume a lot of energy, and that can be quantified both in terms of emissions, carbon emissions, and energy. And a lot of this cost is just about conditioning them, and that's heating, ventilating, maybe cooling them. And with climate change, really, that's just going to increase. So there's a quite cool predictions that I lifted from the Economist showing how the air conditioning usage is going to increase in loads of different areas of the world. And really, I think that the thing to remember with buildings is it's not really like single plastic use or maybe flying. It's not really something you can, it's difficult to cut down on buildings. We need them because that's where we live. So if we want to kind of work on their energy consumptions, we need some clever solutions. So yeah, in this talk, I'll just give a brief overview of what's happening in buildings and why they consume so much energy. I guess the kind of background to this is that we do spend the majority of our time indoors, and that can be at home, in offices, maybe in close transports. And the air that's in those environments can have a big impact on our health and our well-being. So that because it impacts our thermal comfort and also it impacts the quality of the air we breathe inside. So there's maybe a kind of stupid image of thermal comfort, but if you think about it, the buildings we live in, we want to be using properly. And if the thermal comfort is not quite right, you might be a bit too hot and you might not be as productive. Or if we think in the setting of a university, your students might not be able to focus on your lecture as much as you would want. So these are the kinds of things we're trying to look at by looking at thermal comfort. Air quality can be anything from pollutants. That can be, usually we think of pollution as coming from outdoors, but then there's a lot of indoor sources as well. And I think that was brought to the kind of general public through the COVID-19 pandemic. And I lifted one of the slogans there that clearly showed that fresh air is really important. So the way we kind of condition those buildings, there's loads of really different designs and different ways we can heat, cool, and ventilate them. Typically, when I think of ventilation, I kind of think of two extremes. One is kind of naturally ventilated. So that's when you have things like openings, windows, doors, and you kind of use natural forces to drive the flow inside the building. And natural forces, I mean temperature differences, so buoyancy-driven ventilation or wind-driven. And then on the other extreme, you might have mechanically driven ventilation where you're kind of just forcing the air through the space. The reality is most buildings will be somewhere in the middle. If I think of my terraced house, it is kind of hybrid ventilation. So it does have those windows, but then there's also an extract fan, for example, in the bathroom or the kitchen. So there's quite a bit of, variations in that. Something else as well is that sources of heat or cooling can be either distributed, so we can think about underfloor heating, or more localized. So I have a portable heater in my office, for example. And those kinds of sources of buoyancy can be quite varied. And the final thing that probably will matter to this audience is that you can kind of automatically ventilate and cool your buildings. That can be through thermostats or kind of managing your air conditioning system, but it could also be something as simple as a kind of automated window opening, depending on different things. So that's something I kind of wanted to touch more a bit on now. I found, while preparing this talk, I found this really cool guide that you might want to look into, and it's basically building services people do control. And they kind of go through the basics of how does it actually look like in a building. And what I mean here is it kind of goes from anything from your basic thermostat in your house where you set a temperature, and that kind of sets the radiators in your different rooms, or it can be very complex kind of building management systems, so quite big things that manage loads of different types of systems, whether it's heating, cooling, window openings. So one of our big buildings here, for example, has a mix, so has a bit of air conditioning, but then its building management system is also automatically opening windows and that kind of stuff. I guess the main thing maybe for control people to think about is what's it's controlling for. And typically, really, so far, it's mostly been about temperature. So just making sure that you set your thermostat and then your building kind of reaches a certain temperature, and that's how you're trying to keep the occupants happy. More and more, there might be stuff on air quality, and that's maybe looking at carbon dioxide, for example. So in classrooms, there's systems where if it goes above a certain level, then you might start ventilating to try and make sure that the air is kind of being kept fresh. The problem with this approach, and so far, really where there's a need for more research and more work on this, is that it very rarely controls for energy use. So it's not optimal at all. And there's been some of my colleagues working on this have found that buildings quite often cool and heat at the same time, trying to achieve those kind of temperatures. So clearly there's a big problem then. And then if we think back to those figures that I was showing about energy consumption, there's clearly something that should be done there. The thing is, with building, there's a few kind of challenges I want to highlight, and to kind of highlight why control could be difficult and what needs to be kept in mind when trying to think about this problem. The first one is, although engineers like me will tell you that, oh, the ventilation system is very well designed this thing, and this is what we want to do with this building. The building you end up with might not be the one that you designed. And that's because of loads of different things. There's a lot of different people involved at different stages during the building processes. There's different regulations, maybe there's problems with quality control. But basically what it boils down to is if you do want to control your building, you need to understand its performance, and you need to do some kind of system ID to really understand what's going on there. And then of course, buildings are things that exist for very long times, so they can change. Their use and how they function can change over time. And this is an example from our campus where we have a church in the middle that used to be for church purposes, but has now been converted into a lecture and some accommodation. So clearly, I think with the emissions included in building buildings, we want to make sure that we're using them for as long as we can. So that might mean changing how they're being used. And of course, that might mean learning about how that would change your model. The other kind of big challenge, and one that I'm very interested in, is you want to condition this environment, this air, for occupants. And that means quite often you want those occupants to be hot and quite comfortable in the UK in the winter, but you also want them to breathe some good air quality air. And that means that you do end up with some conflicts. A good example was during the pandemic. I think school teachers were told to open wide their windows to make sure to reduce the risk of airborne infection. But then you ended up with problems like this, with pupils freezing, and so just having to wear coats inside classrooms. So clearly not something you would want. And then the opposite is also possible. So this is a case from Belgium where they built this very nice, super well insulated, super energy efficient passive house. And then the occupants started living in it, and they started having a lot of kind of health issues, to the point that the house was kind of declared inhabitable. And that's because there was a problem with how the ventilation system was designed. And basically, because it was so well insulated, you ended up trapping lots of pollutants indoors, and that caused health issues. So clearly there's a balance to be obtained between those two things, and that can be quite challenging. The other challenge, which is one I'm very interested in, is that there's some very complex dynamics happening in buildings. The one I know about particularly is fluid dynamics and buoyancy-driven flows, where you might have zones like this where your pollution might stagnate. And so it's quite interesting. Practically, what this means is it does raise the question of where you should put those sensors. So I've said that you can measure temperature or CO2, but where actually can and should you measure to kind of control the performance of your building that you want to? And so that's, I think, quite an interesting problem. And the last one, which is maybe a bit annoying for engineers sometimes, is the buildings are actually occupied by people. And those people mess up with stuff. So they will do stuff when they get too hot. They will open their windows. And one of my colleagues described those portable fans as like the worst thing that's ever happened, because it messes up with whatever nice model you've had. So that's something to keep in mind. So I didn't want to be all doom and gloom. I think there's one last thing I wanted to touch on, especially with this group of people talking about the grids, is that buildings might also present a very nice opportunity. So when you have thermally massive buildings, that could be potentially a source of energy storage. So this is an example from Sheffield. I'm being quite local. So the Millennium Gallery, that uses a lot of concrete, and that means that it's thermally massive, so it has a very slow thermal response. And that could potentially be a way to kind of store energy when it's more available, to then be released when the grid is under more tension. So I think that was a kind of whistle-stop tour of the problem. Hopefully it's given you a good good overview. And yeah, don't hesitate to get in touch if that sounded interesting. Thanks.
Thank you, Carol. That was really cool. I learned a lot about building management systems. I think if we now shift towards Pablo, and we'll do all the questions at the end. So if anyone's got any questions, we'll do at the end of this session and we'll address them there. That just means that we're going to stick to time quite better. So thank you very much, Carolanne. Now, Pablo, if you want to try and share your screen.
Yes, Ross, thank you. Let's just see if it shares. Does it share?
It does. It does.
It does share. Okay.
Good.
God, what am I doing? Right.
Thank you. The
First
floor
of
is
all,
yours, Pablo.
all right. Thank you, Rose. Thanks for inviting me. I'm really happy to be here. I'm a lecturer now in Sheffield. I've been here for a long time. Now I'm gonna talk to you about a problem that now that we're talking about buildings, that buildings are networks, and we talked about the microgrid that is also network. That something that occurred to me, and I was gonna talk about microgrids like Ross said, but then I thought about this problem that is underlying the control of networks themselves. So I veered toward the plug and play. I'm going to explain what it is and how do we use it in control. Oops. So, as you know, Francesca explained very well, a microgrid is just a connection of loads and generators that are all trying to interconnect, trying to achieve certain goal. But what we are looking at is also that different things can also be networks. For example, these wider power network, we can also have some mechanical networks and some swarms of drones. And the common thing that they all have is that they share something called interconnection. They are all interconnected systems in the sense that they are composed of smaller subsystems that act and react based on how the interconnection affects them. So one of the things we want to think about in this talk is, for example, we have m number of agents and finite number of agents, and in these systems, I call them live systems. The number of agents is varying, so it does change in time. This is especially true for microgrids, where we have components of the microgrid coming in and leaving the network, and that leaves us with a strange conundrum: is how do we design controllers for this thing that is changing? Even from a decentralized point of view, is quite tricky, because we need to take into account the interaction in order to make sense of the global stability properties that we would like to achieve in case of mechanical system, or in case of the microgrids, whether we can actually achieve some voltage and frequency equilibriums. The initial steps were taken in the 80s by Yula Kusera when he tried to parameterize all the controllers, in the sense now we can start changing the system and we will be able to find a controller that fits in there. But this idea of changing elements in a network was, as far as I'm aware, it was stated by Staustrup in this paper in 2009, where he's outlining why it's important to try to have a methodology to handle these problems. And given the state of the microgrids this day and age, it's quite prescient. I am going to keep on. So, but what is plug and play? Let's say we have a network of agents that are all interconnected. We have designed lovely controllers that all are acting locally. And we have designed also a network of controllers that are exchanging information. Usually, and this is what Francesca was talking, in microgrids, there will be an upper layer, but let's stick with this second layer. They're all exchanging information, and the topology of the control network can be slightly different than the topology of the actual network. But in plug and play, we're saying what happens when we miss a system leaves the whole network. How do we redesign these controllers? So, for example, now this system is isolated. What information does it need to be steered towards its equilibrium point? We don't know that a priori. So, what's more, what happens if someone else plugs in? How do we design this extra controller? How do we design the network and information it needs? In this case, for example, we're just mimicking the topology of the network itself. So these are the questions that were troubling me since my PhD days. So in this approach, in this particular talk, we're going to talk about a robust way of handling these problems. And why am I sticking with this slightly more abstract one? Is because the solution to this problem gives us a hint of how to handle these evolving networks. And it might give us some tools and ideas of how to approach these time-varying networks. So we presented this in a paper in Automatic in 2023. And basically, we're looking at some discrete time dynamics that have, I don't know if you can see my pointer. I can see a very nice pointer here, but I'm not sure.
We can see it.
You
At
can
least
see
I
it.
can. Yeah.
Okay, perfect. So we have this lovely nonlinear dynamics that is composed of a local dynamics, nonlinear, and some extra effects from the network on this particular agent or subsystem. I use them interchangeably. So what we basically know is that the effect of the network is quantified by this quantity here, this Wi. And obviously the collection of all of these functions conforms the global dynamics of the network, which may be unknown, may be too big, computation intractable, all the usual suspects. But we want to stick with these smaller problems because we can manage them. The only problem is how do we handle these extra things that we don't know? So my approach, and this is probably a bit of a naive approach, is to say, okay, if we assume that these functions are nice and we sort of have an idea how they look like, and assuming that each age, oh, there's a typo here, this should be you, that all of these agents are constrained within some sets that are sensible, we can sort of estimate how big is the interconnection. So this set here, the size of this set will give us a hint on how this interconnection works and operates. But the problem is, what do we do it? Now we know how big it could be, and this is the part where it's conservative, because it's just overestimating the effect of the interconnection, just taking the worst case scenario. What do we do with this? So basically, we do something called tube-based approach. Is just get the original network plus extra terms that could be nominal. But let's stick with just the dynamics without the effect of interconnection. I will try to bound this in some way, such that we can obtain an error that is bounded to a positive invariant set, a controlled positive invariant set. What do I mean by that? Is that we can find a control law for each error. We can find a control law such that the error will never leave the set. And in fact, we can do something else. We can outer bound it. So find some little constants, A and B, such that these two sets are constrained into one another. So in that way, we can roughly estimate how big the disturbance is. And this is what I mean by a measure of interconnection. The size of this set, it's telling us how much error we're making in trying to just operate each agent locally. Before we go into that, once we have this, our idea is to use MPC to regulate this part of the nominal dynamics, but with a slightly modified problem. We're adding these terms that basically capture the idea of the system being steered towards the origin. So if we start very close to the boundaries of the constraint sets, if at the next successor state we live somewhere in the interior, we're not using the full constraint set anymore, but we're using some smaller bound. So the idea of these alpha bars is just to find the way to capture this idea that we are like shrinking, approaching some target state. And with this knowledge, we can define the control law. Our control law would look, it's very standard tube control law, there's no fancy things here. Basically, the nominal MPC plus the RCI control law evaluated at the error that we're making. And I'm putting this set here, which is basically the sum of all of these constraints. It will be useful for later on in the notation. So what do we have here? And this is the next idea that we thought about. What if these sets are actually shrinking the constraint sets? Because as we've seen, the nominal state is kind of going to a target. So it means that it's going deeper into the interior of the set, we can do something very similar here and think, okay, if the nominal set is shrinking, maybe the real set, the true state, the uncertain one, the one that's affected by the network, is also shrinking. And we want to characterize this shrinking by these alpha. As you see, everything that is nominal and works in the nominal system, I call it alpha bar, and anything that is for the uncertain system, it doesn't have a bar. Doing some algebra, we can find these two scaling factors. They also have dynamics. And look, in these dynamics, we can see the size of the invariant sets and the outcome of the optimization problem. If this were to be one, sorry, this also a bit of a typo. If this were to be one, the alpha does not change. So it's basically saying the nominal system is not shrinking. The true system does not need to shrink. But as soon as we move towards the interior, we start shrinking. And what's interesting here is that as we converge to some steady state, our alphas will change. But now let's think about how we obtained the set of disturbances. They depended on the state constraints. But now if these alphas are changing, so will these sets. So therefore, as we delve deeper and deeper into the interior of the constraint sets towards our objective, so will the interconnection of the system will become weaker and weaker. It's basically a translation of the system having more room to play, more control authority. It doesn't have to counteract the effects of the interconnection. So we've noticed this idea and we said, maybe we can use some measure of robustness to study the problem. And that's where it comes collisional control. Because when we have a group of agents, we not only have decentralized and centralized control, we can also have things in between, different partitions and different, this is what I call notions of cooperation amongst agents. And what's more importantly, there's some notion of order in this set. This set is in fact a partially ordered set, which basically says that you can move from this completely decentralized partition to, for example, this one, where only agent 1 and 2 are cooperating, and the other ones are using some more aggressive robustness, and these are taking into account more information. And with this way, we can allow ourselves playing with how the interconnection is being handled here. Again, here I show another chain, but there's also some other sets that cannot be easily compared, and these are called anti-chains. So what is a coalition, essentially? Coalition is nothing but a partition of the big M into subsets. So what do we want from these subsets? Some standard assumptions, like they are non-overlapping. All the coalitions joined together recreate the original set. But what's more important is that the coalition, this grouping of agents, we can group the dynamics equally, and we can represent the disturbances seen by a coalition in the same way. So from a dynamics perspective, they have exactly the same behavior as the decentralized partition. The only thing that would change is the regions of attraction and the way they are handling the coupling between them. Because these quantities W's will shrink or become bigger depending on the case. So oops, I think some bit of notation here. So what we basically have is that the region of attraction of all this network will be then the region of attraction of a nominal problem plus the effect of the constraint sets. And obviously, since we're looking at a particular problem, at a particular network, we're interested in the Cartesian product of all of these. So if somehow we make this set invariant, we can say that our collision is recursively feasible. So what this means essentially, if the state, we can find solution of these MPC optimization problems, because for each of these coalitions will have a separate optimization problem. And now, how do we apply this to plug and play? This is very important, is to know that we start from this perspective that we know if we could design sets at the initial for a decentralized partition, let's say, which is basically when these sets are all quite big, we will have a notion of how big, like this will be like the most robust you need to be, because as the moment the system starts evolving towards its equilibrium point, this disturbance will shrink. So if you're robust initially, you'll have more room to cope with more disturbances as you move on. And what's more, what we notice is this scaling factor that we have defined, a mention of how robust we are. And not only that, but this difference between the current and the future scaling factor will give us a rate of change, a rate of convergence towards towards a given steady state. And we have in that paper some existence types proof that we can guarantee the feasibility and of switching between different groupings of agents under some conditions. So let's use this one and let's see how it works within our framework. So first of all, if we remove an agent, what we're basically doing is removing disturbance from the rest of the network. So basically, under our point of view of robustness, this improves the performance of the network. And because we have entered the interior of the constraint sets, we'll be able to find solutions to our optimization problems. Now, the problem is what happens when we have to add an extra agent, another wind turbine has joined the network, for example. We found out that under this approach, this cannot happen immediately because the controllers will not have enough control authority to be able to cope with this change. We found some dwell time type proofs to guarantee that when this is feasible. And what's interesting is that we can use those scaling factors as a measure of how long it needs to be. How long is sufficient for a disturbance to be small enough such that it can be incorporated. And also we need to satisfy some condition like this that basically says the disturbance of the network plus the disturbance given by the extra agent needs to be included in a previous disturbance set for a bigger alpha. And this gamma is basically it's related to the size of the original interconnection that we had before. So if we have these conditions satisfied, then we can conclude that we can actually remove systems and add subsystems without the need to modify the controller itself. We just need to add the control law of the system that is being added. I know for the interest of time. What's more, we have managed to put a Lyapunov type function that now takes into account the evolution of the shrinking of the sets. So basically, why do we include this? Because the sets and the problem of distributing a problem, the issue of the distribution of a problem is that it introduces some uncertainty. And we cannot really go to the origin. Where we really go is a neighborhood that looks like this. I know it's a bit of a mouthful of notation, but it's the price we pay of using distributed control, that we no longer get there, but we can always use stuff like Lasalle's invariance principle to guarantee that given if we have designed our RCI's control laws nicely, we can actually get to some desired state. But in principle, we don't really need to. will be constrained on this set, on this particular neighborhood. I'll give you an example very quickly. It's a mechanical network. I know it was supposed to be microgrids, but this was the most intuitive because of how they perform. So we have 4 tracks, and we will add one at some point. And how do we regulate these tracks to a given equilibrium state is given by this. So at the beginning, they all cooperate and they form the grand coalition. And as time goes by, agents don't need to cooperate anymore until it comes to a point where they stop cooperating because they have achieved. And at time 16, we see how a new agent has been added to the network. And now in agent 3 to 1, they are unmoved by this change. But they're basically, the only one who needs to worry about it is agent 4, because 4 is the only one coupled to 5, right? And 5 will be a disturbance to 4 only. And here I show you how these sets and the tubes are shrinking as time goes by. You could see where, for example, the new set has been added. I have an evolution of the scaling factors, how they change and how they don't converge quite to 0, but there's still some artificial noise lingering. And what's more important here, how the volumes of the constraint set have shrunk. And this is also a tool that we use to prove the stability of this approach, that the fact that these dynamics of the scaling factors are converging allows us to guarantee that the state will be sucked in towards its equilibrium. We're applying now these ideas to microgrids, particularly to peer-to-peer trading, where you have agents that come in and go. But the notions of equilibrium are slightly more confusing in this case. So in a bit of conclusions, now we can use robustness to handle reconfigurability, element joining. We can do it if we have enough robustness margin, and that's the key. The key breakthrough in this analysis was basically the feasibility, thinking about feasibility when we don't break our optimization problems, and how the structure of the set of partitions affects which partitions are available. And the scaling factors have helped us immensely to crack this nut. And yeah, thank you.
Thank you, Pablo. That was really cool. I don't want to know how long you took on the text figures, but okay, so does anyone have any questions for our three speakers? If they do, can they either raise their hands or put some text into the chat box? And if you can we'll do a bit of questions and then we'll go through some sort of more questions that we prepared of our panel session. So Francesca, I mean, for your learning algorithms, do you care about kind of robustness at all, or like do you constrain the neural network in some way to satisfy that everything's going to work out, or do you just let it train and it comes to the right good predictive model or?
Well, we are not forcing the just in the energy management scheduling problem, we don't have the problem of stability.
Okay.
So that's a point. We are working at extending that problem to a general control problem, and of course, in that case, we would need to consider that aspect too. But the idea is to take into account, of course, of the uncertainty that we have in the predictions in order to build the robust controller. So the interesting aspect is that in the optimization layer that you can embed as a differentiable optimization layer in the neural network, you can define constraints. So you can also define some constraints for robustness the controller as well. So that's the interesting part. So yeah, in this sense, you can consider robustness in the architecture. Moreover, we can, of course, you can define the constraints there, and you can guarantee the satisfaction of the constraints that you define in the architecture. Finally, by using the uncertainty quantification tool that I've briefly explained for the resilience part, you could even somehow give additional theoretical guarantees on how much the system, the controller is robust to changes in the profiles.
Okay.
I mean, I could articulate more, but of course.
No. I could spend half an hour just asking you questions, I think, about that paper. So
we can have a chat later, definitely.
Because, sorry, I mean, so second question, I mean, do you find that, because I'm quite used to seeing an optimization layer, I mean, that's quite natural to control engineers. Do you find that as a neural network kind of architecture or as a block, it's more, as you know, sample if it was just a random neural network, say a ResNet or something, do you think having the OptNet stuff there is, what are the benefits of that? What are the...
Well, the benefits in our case are mainly that we can train the network directly targeting the control performance instead of targeting the time series mean square error for the prediction error. So we have seen that that's a big advantage because it allows to take into account of uncertainty in the model, even if we don't consider that. So we have seen that the neural network implicitly learns more than just the uncertain profiles of load, price, and generation. And it's actually able to somehow learn how to optimize the controller even without, I mean, from data, even if we are not explicitly asking the prediction to do that.
Okay.
I have one little question about that last sentence of optimizing the controller. By that means tuning the cost or tuning the constraints, because those are the two ultimate things that characterize an MPC controller, right?
Yes. So in the case of the energy management system, the predicted profiles enter in the optimization problem, both in the cost function and in the constraints as parameters. They do not enter directly in the model, in the specific formulation that we have.
Yeah.
Even if you could design an architecture where those enter also in the model. By targeting the control performance, I mean that we are using, in the energy management case, we are using the cost of the boat power from the grid in order as a performance indicator for to train the neural network. So,
okay.
Yeah.
Thank you.
Yeah.
So going towards more, we got a question in the chat. So this is from Parfait Lundula. Thank you for the question. So for Pablo, I mean, so I'll read it out and then, so how conservative is the proposed methodology when it's applied to dynamics of power system devices such as wind farms or synchronous generators? That's question one, I think.
Yeah. Thank you. Thanks for the question. The issue is what happens at the beginning, because the scaling factors allow us to sort of add an extra degree of freedom in quantifying the interconnection between these things. I have devoted a good chunk of time thinking about what are the alternative uses and characterizations of interconnection, not just using invariant sets. But for example, I found that if in the case of power networks per se, DC microgrids, you could use the Laplacian properties, the sense that the kernel of the Laplacian is an attractive set for the whole network. So you'll know that the states will try to be together. And based on that, you can generate bounds that will allow you to quantify how much interactions you're having. So that's another way of measuring how much interaction you have. In terms of synchronous generator, I've applied this idea. Well, it's as conservative as your description of the uncertainty is. That basically that would be my answer.
Great. Any more questions from the audience? Oh, got a second one. So is the plug and play property related to the stability of the network or the performance, or both?
Both, because what you have is, if you wouldn't have any structural changes in the network, what you want to do is to drive it to its equilibrium state, right? Being 220 volts, 50 hertz, or at a point where there's no load movements. But now when you have an event that basically is changing fundamentally how the system is interconnected, the system will react to that. So you need to find a way to drive the system again back to its equilibrium state. So the plug and play problem is asking you, how do you do that without redesigning everything? We don't want to redesign controllers again. So what's the best way to do it? Yeah, so that's it basically.
Great. Yeah, if anyone just wants to leave something in the chat and either read it out, or you can nominate me to read it out, or just raise your hand. I mean, I think as well, if I could ask one to Carolanne or Francesca. I mean, it's kind of a bigger question about women in control, really. So I think probably in this call, and at least in all control and departments involving control engineers, it's quite male focused. So could I ask kind of how can we change, or how can we improve things for kind of for making it more accessible for women in control? So Carol, do you have an answer?
Well, I can confirm that I think control is not great, and it might be one of the worst for engineering. So I'm an admissions tutor for aerospace in Sheffield, and I was looking at the different kind of programs, and civil engineering is a bit better, but then yeah, control EEE was doing quite badly. And it's not a Sheffield problem. It seems to be quite widespread. It was the same when I did my undergrads. Yeah, I think if there was a simple solution, it would have been fixed. I mean, the way I think about it, there's kind of two problems. One is kind of recruiting, so convincing young girls that STEM is interesting and kind of increasing the number of girls who study maths and physics in school. So that's quite low already. So if you start with a smaller pool, then of course you'll end up with less female engineers. And then there's also the retention. So once you do have female students, how do you convince them to go into research and then to stay in universities? So those are my thoughts, but yeah, no simple solution.
Yeah. Francesca, do you have anything to add? I mean, it's...
Well, yeah, I agree that, well, the problem is not only in control, and of course it's a generalized problem in STEM, mathematics related, let's say. Well, it's a problem in general to recruit or to attract people working in STEM, and specifically female students. Yeah, what can be done? I mean, we are working in that. As you might know, I'm also involved in the lead of the EDI group for the ACE network, so we are trying to explore these aspects. Definitely outreach and working with younger students, that's something that we could all do and try to attract people. I think it's also a cultural problem, so I think that what everyone could do is really also thinking about how children that we have or that we will have, how do we make our discipline interesting for for the younger generation in general. Then what we are considering are aspects on how it might be more difficult for women or in general for EDR or minorities to engage with industry, or how there are difficulties sometimes for parents in general, so not only women, in for example participating to conferences. So how can we be more inclusive in general of people with families or people with children? That's something that I think we can work in our institutions, in our groups, to try and be more inclusive in this sense.
Yeah. So I have gone into conferences as a sea of people that look like me. It's not great, but trying to change that. Yeah. Because I know
It's low, but probably
Mm.
everyone can do something in their own realities.
Yeah. I mean, again, Francesca, maybe. I mean, how do you find working with industry? So if you've got these great, new algorithms for learning, how would you? What's your experience of trying to embed that back into industry and convincing them that these new control ideas should actually can save them money, I guess, or how you felt about that?
Well, definitely for control engineers, there is sometimes the difficulties in showing the impact of our methodologies, of our ideas. So definitely, I think that an important aspect is to drive our research, having the two focus, of course, theoretical development, but also having meaningful problems and application-driven motivating our research. That's how I find it, let's say, interesting for me, and of course how to improve the chances to get collaboration with external partners and industry specifically. There is also a bit of a balance between trying to understand what are the goals, the needs of the industry. That's what they've been working on. Sometimes it might be easier with the companies, small companies. They might have specific problems, but then they might have more constraints on budget and so on. So I think it's a difficult environment in the sense that engagement with industry, it's not easy. It's a lot about personal relationships and how to build them in the long term to sustain them. Sometimes it's easier when you inherit or you have already contact there, then things get much easier. Than establishing new collaborations could be tougher. But at least in our institution, we have quite a lot of support in how to direct the needs of industries to the academics and try to match expertise with industries. That's how I'm trying to work on this.
Very good. How about you, Carol? I mean, with the building, the civil, do you think they're open to you playing around with their building control systems, or I don't know? I have heard of a rumor that someone had a student project to design the control system for their building, and it just it just fell apart. So how do you find that?
Yeah, I think it's complex because there's so many people involved. So if you were to go and play with the building systems control, let's say, the people who make the BMS and management system are probably different to the people who made, I don't know, say the ventilation unit, different to the people who made the boiler, who are not the same people who installed it and probably not the same people who manage it day to day. So there's loads of different moving parts. And so working at the university, for example, one of our building, the Diamonds, has loads of sensors and is collecting loads of data. I'm still not sure how you access this data and who actually knows like where it's stored and then also what it means. So it can start being very complex problems, which is so to make it so easy that you could get someone to play around with it is it's quite a challenge. And then of course I didn't talk about the users, but if you were teaching in that building, I'm not sure you would be happy if there was a BN student who suddenly decided to set the temperature at 10 degrees or something. And I think your students would also not enjoy it. So yeah.
I'm tempted to make it coursework. They have to, and if they mess up, then they have to sit in a lecture that's too hot and it's their own fault or something.
That might be a good incentive.
Yeah. Anyway, yeah, I don't know. It's yeah, it's interesting. Yeah, so I mean, I guess for Pablo and Francesca, I mean, where do you see there's a lot of learning now? I mean, how do you see that the control interacting with these new learning environments? I mean, even specific for these applications, do you feel that what are the things that we should be looking out for or adapting to actually getting the best out of learning and control, plus embedding it in some challenging industries?
I can go first if you want, Francesca.
Okay.
I think the trend is clear, isn't it? This whole neural network learning data is here to stay, especially now that we have a huge spike in the computational power that we have at our disposals. Not even like we don't need am I being? No, yes. Not even having the need of huge hardware to train certain neural network models. From my experience, what control can bring to all these ideas is this notion of guarantees and make sure that things make sense in some way, that we define some criteria and according to the criteria make sense. Because the way I see most of the learning algorithm is basically some sort of map, right? And how do we make sense of this map? We can use, that's where the control ideas come into play. And now the conversed inclusion, from at least from my perspective, it has huge potential. So for example, crafting glosses for NPCs, estimating interconnections, finding equivalences between NPC and neural networks. These kind of things are super interesting to me from both a theoretical perspective and as an enabler to do far more interesting things in the applications that we have in, because it opens the floodgates to so many more ideas that previously were not really. It was almost impossible to do them, but now we can.
Thank you. Yeah.
Yeah, those are my 2 cents.
They're more than 2 cents. They're 10 cents.
I agree on the many opportunities that come from data, machine learning, AI. Definitely, it's amazing what we can achieve. My position, my personal opinion is a bit on the integration of data-driven and model-based. I don't see, well, maybe we will go at some point totally fully data-driven based, but I have some concerns on that side, coming also from my background is a lot on reliability, safety. I'm a bit more tepid on the learning based. I think that we need to be careful on what are also the potential vulnerabilities on that. And one thing that I would say is that we need to be careful also at not completely forgetting what we know. I mean, we have a lot of history and a lot of results and knowledge, which is based on theory and models and physics. I don't see it wise throwing completely away everything. So yeah, I see the future more about the balance and the combination from taking all these great opportunities, adaptability, personalization, performance, and everything, thanks also to the computational power, growing computational power, and so on. But I think that I see control and the aspects of more traditional, let's say, theory that we have working to support each other and make sure that we get things right. So that especially when we talk about safety critical systems where we want to have guarantees about their functioning. And also talking with some industrial partners or people from industry, I see a more cautious approach in machine learning AI-based techniques. Yeah, that's nice, but can we apply it? Depends. So yeah, I'm a bit in the middle. I like to use both.
Yeah, I think that's wise. I think that's where it's going. Well, thank you all. I think we might have, I said a 10-minute break. I might cut that down to 2 minutes. Enough for me to grab a cup of tea, really. And then we'll start the session 2. So if we come back in 2 minutes time, then we'll have Volkan, Brady, Noel, and Yuanbo, and Adrien as well, actually. So I know I've overran. I could have predicted that from the start, but we'll try and have a shorter break and then come back later on, where we're going to learn more about batteries and control. Exciting. All right, see you in 2 minutes. Okay. I've got my tea. Do we have Volkan? Ah, good.
Hello, Ross. Can you hear me? Can you see me?
Yes,
Hello?
and yes. Yes, perfect.
Yes. Okay. I'm here with my turtle, so should be fine.
I'd expect nothing
Uh,
less.
So, how do I share my screen? Okay. It has been some time not using the
So the
things.
square with the arrow in the middle.
Yeah. Okay. Okay. Can you see my screen right now?
Yes, we can.
Yeah. Okay. That's wonderful.
So
yeah.
so welcome to session 2 of this webinar for the ACE network. So this session is all about control for batteries. So this is kind of home turf for me, really. And the first speaker is Volkan Kumtepeli. I hope I said that. I've never said your second name, Volkan. It's always ever been your first name. And who did his PhD in Singapore and has been in Oxford as a postdoc for a couple of years now. And he's going to be telling us, about how to make money with batteries, which is quite interesting. So please, go ahead, Volkan.
Okay. Thank you very much, Ross, for your kind introduction for this nice opportunity. Hello, everyone. Hope you are doing all very well. I'm Volkan Kumtepeli, a senior researcher at the Battery Intelligence Lab at the University of Oxford. Today, I will be virtually presenting our work on determining the value of energy storage and how depreciation cost alone may fail to capture the opportunity costs. So let's start. And on the map, you can see our lab. Maybe we need to zoom a little bit more. And now it's more visible. So if we zoom even more, you can also see our wonderful team inside the lab. And this is an old photo, and we have some different people right now, but we will have to have a new group photo very soon, hopefully. And so in this lab, we are working on various areas, I would say, and battery state estimation for a tighter control, and some degradation modeling for higher financial returns, and grid scale system optimization and data analysis, or PAC modeling. And you will hear more from my colleagues in the next presentation, so they will give you more, about this estimation and everything. And here in this graphic, at the top, you see the state of health, and below you see the corresponding financial returns. So if you use battery a lot, your battery dies early, and you don't get much financial returns. If you use it lightly, your battery dies much later, but again, you don't get much financial returns because you didn't use it. So you need to find a balanced strategy to preserve the battery lifetime while getting most of the profit, where our aim is to get the maximum attainable profit, which is shown by the blue star here on the bottom graphic. So let's consider an arbitrage application where your objective is to maximize the total profit given the energy prices subject to the battery dynamics and end-of-life constraints. So this problem is a little bit difficult. Why? Because it spans to the whole life of the battery, such as 20 years, maybe, in these days, people are talking about 50-year batteries, 100-year batteries, or million-mile batteries, who knows? So even, however, even with more powerful machines, we still lacked reliable data for 20 years. So what we do is we can divide this problem into smaller chunks, and also removing the state of health constraints, as it won't change much in several days, let's say. So we will be solving these problems in the blue boxes. So now the optimizer, this problem is, doesn't know that battery is going to die someday because it's just a 2 or 3 days optimization. So it can make greedy decisions to chase small profits using battery at extreme conditions. then why not maximize profit per capacity? This works. However, it still is making local decisions, but we want to optimize overall profit over overall degradation. So we have our usual formula, which could also be considered as the config-fied version of the previous formula. However, we introduce one more parameter as cost of aging, and so our story just begins. Let's start by looking at the Q loss and how we can define it. So in the literature, battery modeling is extensively discussed topic, from simple to generic or empirical models to advanced semi-empirical or physics-based models, or probably in these days, machine learning models. So I devoted my PhD building complex mixed integer models to include aging in mathematical optimization. So on the right, you see my PhD masterpiece. Best case, you get several more years out of the battery. Meanwhile, researchers in the other labs got similar results with physics-based models and experimentally validated these. Here, it is also possible to see the importance of revenue per aging, which was the second formulation in the previous slide, the slope of the curve. So how much difference does it make? I would say that our numbers are between like a 20–30% increase in the revenue and the reduction in the degradation, which was also similar numbers in the lab in the Oxford done by the Jorn Reines, I would say. So it's pretty consistent. But this is only the half of the story. Even when we modeled the battery aging, we don't know its price. What could it be? The price you bought the battery, the price you are going to replace the battery, or some arbitrary value. So we have reasons to believe that it is expected value of future returns per degradation. So let's test this hypothesis with a simple model comprised of calendar and cycle aging. So the Q loss is the sum of these two, and we select the degradation price as the price you bought the battery, as it is the widely used in the literature. As Q loss is a simple keys-wise affine model, we can perfectly represent it in the optimization, eliminating any artifacts due to the difference between the forward model and the optimization, and achieving the goal of advanced battery models. So normally, why do we use advanced battery models? Because you want to represent the aging as accurate as possible. So let's say our forward model or aging model is very simple. Then you take that simple model into our, how can I say, optimizer, so it is perfectly represented. Then the perturb or aging model with some lambda multipliers to see the best cost. So we are just perturbing the cost of the battery aging. And we simulate the optimization and the forward model in a loop until we reach the end of life, which is the MPC, classical receding horizon scheme, and then calculate the net present value and the profitability index of the application. So on the left, you can see the results regarding the parameter sweep with zero interest rate consideration, where the yellow line shows the both lambdas are equal and the perturb at the same time. And here we achieve the best profit when the lambda value is around 6. So this is a wonderful result, because if the C investment choice from the previous slide, like if the price you bought the battery was the right choice to have the penalty for the battery aging, then we would have received the best profit when the lambda was 1. However, we achieved it when the lambda is 6. So on the right, you see the same graph, but when the interest rate is 5%, so we investigate the effect of the interest rate, where the optimal lambda is now around 3. So these results also support our hypothesis, as the lambda we see is the same as our profitability index. Let's stop here for a moment and think. We have many people work on aging-aware optimization, and they are reporting increase in the profit thanks to the advanced battery models. I'm one of them. And now I realize if I just made a typo and multiplied my aging function by 3, and I would have gotten another 30% increase on top of my already 30% increase in the profitability. So this result was very surprising to me. When we started this study, I was curious about the difference between the effects of calendar and cycle aging, considering that maybe if you have too much calendar aging, then you have to use your battery more, otherwise it would die anyway. So this was the initial point where the study emerged. So this is, I guess, still holds, but our aging functions are too simplified to make a conclusive decision on this part. So we are still working on it. And therefore, we would only focus on the total Q loss for this study. Let's see how it changes for different interest rates. So our hypothesis still holds for higher interest rates with a little bit small shift. And by adding a small correction factor, we see the relationship between the optimal lambda and profitability index hold. If you ask why there is a correction factor, some people say that it is because we are calculating the, how can I say, profitability index with starting from 0 or 1. But we are still actively discussing, especially with Ross from Sheffield, about finding the root cause of this situation. So, of course, knowing the value of lambda by parameter sweep doesn't help us very much. So therefore, we would like to see if we can estimate it online. So when you're using the battery, can you just estimate this parameter, which would be valuable for us? So here we have a basic moving average, moving horizon estimation. And you set the lambda 0 initially, so you use the battery a lot. Then start rolling horizon optimization. And each run we will obtain the weekly revenue and aging. Then we just calculate the lambda value for that week and just take the moving average of the last M weeks, let's say. And on the right, now you see the result of this basic estimator with weekly lambda estimates below is mostly converging after 2 weeks and slowly converges to, a value of 6. Which was the value we found by the sweep study. And it's also possible to see in the long term, lambda is decreasing as the battery capacity decreases. So this was another observation. And so we have shown that after buying the battery, its value is determined by its future profitability. So you don't use the battery initial investment cost anymore, which is directly influenced by possible use cases. So for different applications, arbitrage, frequency regulations, other things. So you may have to tune your, lambda parameters accordingly, depending on the profitability of the application. So even we initially pay a lot for the battery, we still have to use the battery. If you just, let's say you paid 100 millions for your very small battery, yeah, you may be rich, you can do that. But if you put this 100 million pounds of a cost in your optimizer won't be using the battery anymore. So, so what we can say is, as our title says, depreciation cost alone is a poor proxy to eliminate the myopic behavior of short-term optimization. So a better method could be an adaptive estimation to dynamically find this parameter. I should also note that this study is an initial study, so we are still working on it. But mostly I'm also doing other stuff like writing proposals and everything, so I couldn't focus on this, I'm sorry. So we can use some kind of more detailed methods like optimality conditions, some bi-level optimizations, some other things, and look at the nonlinearities, knee point effects, or maybe second life use cases of some pessimistic scenarios like conditional very at-risk optimization. But I should say that like this optimization method is currently used by several institutions as far as I've received the emails from them. For example, when you have two different batteries with two different state of health, how would you optimize that kind of a system? So you can assign two different lambdas to the each battery pack, and you dynamically try to estimate two different lambdas. This is one of the things I think my colleagues from Technical University of Munich and Kempten are working on it. So I don't know the current status of the work, but yeah, they are working on it. Nevertheless, we are hoping that our study will be useful for other researchers for not just understanding the value of the battery, also as we support the idea of estimation, we may take the adaptive algorithm in the further, a step further, like use some kind of a Bayesian optimization, machine learning methods, or you can just say that if not the the battery health, but the multiplication of battery health, and it is the profitability from the application is the one we need, then we can use a combined estimation, just the value of the battery rather than the the health of the battery, or like we may eliminate the need for some like very advanced physics-based models. So if we just have to include the estimation anyway, and we can shift our computational power to be used complexities in the optimal power flow. And thank you very much for listening to me. And for more information, our paper and code are publicly available, as you see here, or you can send us an email, or you can visit us here in Oxford. I wish you a very happy day and the rest of the webinar. Thank you.
Thank you, Volkan. That's great.
I stop sharing.
In the interest of time, I think we should move to Brady. I still want to analytically find why that lambda is equal to whatever it is, pi over 1 plus I. If anyone wants to help me try and solve that, or help me and Volkan, sorry, try and solve that, please. Yeah. I think it's possible, but you know how much I love this stuff, so that's great.
Your equations were wonderful. I still need to work on them a little bit more. So I will definitely have another meeting to discuss this topic with you.
Please do.
Thank you.
All right. So thank you, Volkan. If we can now, Brady, can you share your slides? Perfect. So Brady, please, the floor is yours.
Perfect. Thank you so much, Ross, for the invitation, and thank you, Volkan, for the introduction to our group, so I can move past that as well. So today I'm going to talk about some work that we've been doing around system identification for conventional battery models that are used for prediction, degradation, and kind of cost awareness, as Volkan has previously discussed. So this work is in collaboration with some colleagues inside of our group, but also there's quite a few external parties that we have collaborating on this. So essentially what I'm going to discuss is PyBop, which is a battery model optimization and parameterization framework. The kind of selling point for this is you have data and you want parameters. So from the classical system identification perspective, we have an underlying forward model, and we're trying to identify the corresponding parameters for that forward model. This is not very clear for a large amount of the battery models that we investigate, mostly because the varying scales of those models can be kind of abstracted to identifiability problems, or we have issues where the underlying data doesn't excite the system the way that we want. And because there is such a wide range of battery models available, one of the challenges we have as a field is to properly identify those models and provide that identification to industry partners, or even to corresponding researchers to really get a better understanding of the underlying physics that might be happening, or useful for predictive tools where we want to run real time or something like that. So the selling point here is you might have some experimental battery data, or you might not. You just want to investigate with some synthetic data, but an underlying identification is not available. So we don't have that identification for the specific cell in question, right? We have a battery, we want to identify a forward model with that. you aren't sure what the data is supposed to look like. You know, we don't know what sort of excitations will give us an underlying identification of the model. Or you might be missing some data, which is very common in our field, where you have some small subset of data that you think might identify a model in a rough way, but you aren't sure whether or not that is going down the right path, or what sort of additional data you would need to get a better identification of the model. So all of those points align with PyBop, and the goal here being to provide a nice framework inside of the battery modeling field, so that we can closely couple with a very common empirical and physics-based modeling package. So PyBam inside of the bottom here, if you can see my cursor, is a very widely utilized numerical modeling framework inside of Python, where we can provide an ability to create essentially PDE, ODE systems for electrochemical models, but as well provides a nice interface for us as a field to align on canonical models, so we can identify the underlying parameters for said model in a very efficient and well reproducible way. So the kind of overall view here is we go from left to right, where we have some experimental data. We interface with PyBop. PyBop uses the underlying PyBam models, or the user provides us with a PyBam-esque model. And then what we can do with that is do system identification or design optimization, where the user might want to investigate how the corresponding model could be improved, or the underlying physical parameters could be improved for better usage under their operating conditions. So in the kind of the theme of green energy, you can imagine we have some grid storage, and we want to determine, you know, which corresponding parameters or physical dynamics of the cell need to be improved for us to gain more response from the system or lower degradation, all of which can be done synthetically or online before we can move to the lab to try to experiment with those. So the first kind of aspect that we solve in PyBop is the system ID interface. And this is done through essentially coupling the PyBam models in such a way that the user can provide us with observations, and then we can give them the underlying parameter set that they're interested in. So on the right, this is essentially an electrochemical model where we have the cell at rest, we apply some current, we get some charge transfer resistance here, so the cell kind of dips in open circuit potential, or terminal potential, and then we remove the current and it relaxes back to just a bit below where we were at before. So the green trace here provides us with the identified model, where the orange is some observations that we get. So this is the kind of goal that we're trying to provide to users, so that they can better align their usage with focusing on whether or not they've selected the right parameters, and whether or not the parameters themselves are identifiable. So a quick overview here is that, you know, we can fit, you know, almost any PyBam style model, and this can be, you know, empirical or electrochemical. The fit is usually on the order of minutes, and it can be even faster given some of the speedups that we have. But we offer both point-based and distribution-based methods, so you can kind of provide uncertainty in your identified methods as well. And there isn't really a technical limit, but identifiability is the true question and the bane of everyone's existence with modeling. Similarly, we can you know, flip the optimization problem so that we're now doing design optimization. So that instead of trying to minimize some likelihood function, we're now trying to maximize a physical representation or an operating condition. So you can see, you know, on the right, we start with some initial parameters, and then we essentially select a cost model, or a cost function that can be anywhere from something that is very common in our fields, such as energy density, to whatever metric you want to create. We provide that as an interface to users, and then we can optimize across that cost function to gain essentially a better selection of parameter values for us to maximize the given cost value in this situation. So we end up with a new optimized value for the underlying parameters that provide us with a lot more energy for a given operating condition, right? So the operating condition is the exact same between these two traces. And then kind of across PyBop in general, we really structured the package so that fast optimization is one of the things that we really care about. So we have multi-step kind of baked in parallelization across many cores in our code base, but also kind of looking towards improving convergence through transformations of varying scale inputs. So you might be optimizing parameters on the order of micrometers at the same time, something on the order of tens of thousands. So we provide a lot of interface mechanisms for users to have stable convergence, or at least the ability for them to see convergence issues quite early on. And what this essentially looks like from the optimizer perspective is this cost landscape. So in this situation, the parameters that we're trying to optimize are some physical representation of the electrode thickness. So on the positive side, so we want to know how thick we should make the cathodes. And then on the left side, y-axis here, what we have is the amount of active material, like electrochemically active material per unit volume inside of that electrode. So we can kind of see, we start the optimizer at this kind of random initial condition, and we end up with this ridge-like function in our cost landscape. And the goal here is for the optimizer to find some truly optimal representation of the numbers. And then the final step is for us to look towards validating this, which would involve manufacturing the cell and then comparing this synthetic optimization to that value. So I realize that's maybe a little bit outside the control realm, but I just wanted to discuss it while we were here. So the bigger effort that we've been trying to do is build the underlying PyBand models in such a way that allows us to have interoperability between the user space and the ability for these models to be kind of both fit for identification, but also design optimization. So we offer the very standard electrochemical models. So this is something like a multi-particle representation for the electrodes, where you have some sort of PDE system down to a single ODE style model. Sorry for the acronyms here. This is something that was presented for a different conference, but I think the underlying the point to get across here is that the identification process can happen on multiple orders of models. So we can identify reduced order models and all the way up to the full order representation. The thing that we found very interesting early on was that the field itself identifies parameters kind of independent of models at times. So one of the challenges that we've had to infiltrate the field itself is getting through the understanding that the corresponding parameter set and the model need to go hand in hand when we're doing identification for the forward model. So if we identify on something like an SPM, we need to make sure that the usage of that model and that parameter set is with an SPM and not on the higher order models in some underlying situations. Furthermore, the additional thing that most people end up wanting to do is do multi-operational fitting. So you might have a functional form for an underlying parameter that is interpolated across some operating condition, or you might have a single value that you're trying to infer or identify from a mixture of observations. So inside of PyBop, we can do both of those things, and we offer that as kind of a clear interface to the end user. On the right, you'll see we have kind of 3 different applied currents. So this is the same cell that we're applying varying levels of current to. We start at the same initial condition, and then we have the same end condition. And what we're trying to do is identify a single parameter from these 3 different observations, or a single value of a parameter of multiple parameters. However, the ability to do a functional fit across something like states of charge, temperature, and applied current is something that we tend to offer as a solution for the situations where the user might want a more empirical model that doesn't necessarily capture the underlying physics and the physical dynamics of the system. So we can also investigate both time series and frequency-based identification or model predictions. So one of the things that a colleague of mine who will be speaking next will discuss in further detail is the ability for us to create an impedance spectrum and then do identification off of those spectrum. So on the left, I show kind of a single operating condition. So we're at a fully charged cell. We can oscillate that cell and get this spectrum out of it, and then we can do identification with that. And then on the right, we can do kind of a multi-operating condition or multi-state identification process where we go across the full operating regime. And what we essentially can get from that is an underlying difference in the cost landscapes, or at least provide to the end user how the varying levels of information might inform the optimization task at hand. So you can see on the right, we have kind of a more complex cost landscape where the optimizer is started at this initial position and then kind of moved south towards a lower contact resistance before trending towards a smaller particle diffusivity. But on the identified impedance spectrum, we end up with a more linear representation due to the single operating condition that we're at, and we spend less time in the underlying in this kind of regime area here. So this is all provided to the user kind of early on so that you can understand what the convergence looks like across the system. So up until this point, we've been discussing point estimates, but really what we'd like to do is capture some uncertainty in the underlying identification process. So we want to spend less time talking about a single point and more time talking about a distribution across those points. And this is possible inside of PyBop through our sampling methods. So we have Monte Carlo sampling kind of built into the underlying framework and allows us to essentially create a Bayesian approach to identification or support a Bayesian hypothesis through the identification and give end users the ability to look at a range of parameters and upper and lower confidence intervals off of those ranges. So just a quick example as I wrap up here, I wanted to discuss how we investigate identifiability inside of the PyBop framework. And this is available through a couple of different metrics that we provide. So we can look at posterior distribution statistics. We can also take a look at the Hessian or the Fisher information matrices. And then finally, we provide both global and local sensitivities. So in this example, we're essentially going to have a cell at rest. We're going to do a pulse for a discharge period, and then we're going to rest. And this is the observation that we'll be using for identification. And we're going to do it at two different states of charge. So one at very high charge, and then another one at very low charge. For this SPME model, so an electrochemical model, and we're going to try to identify this volume fraction for both electrodes. So this is the amount of active material and kind of a unit square in the electrode. And essentially what we can get from this is a perspective to the user or position to the user of a numerical representation of how identifiable each of the parameters is, or the contribution that each parameter has to the underlying identification process. So if we look at something like global sensitivity, at 15% state of charge, so at a very low state of charge, the first parameter, which is the positive electrode, is very sensitive. However, the second one has a lower sensitivity to the model output or the signal that we're identifying off of. Versus at higher states of charge, this is flipped. So we know that the identification for each of those parameters is a function of the operating state or the state of charge. And we need to keep that in mind when we're identifying those underlying parameters. Fisher information points to the same direction. We have very sharp Fisher information at low states of charge, but it dulls out and becomes not identifiable or lower identifiability at high states of charge for the parameters. And the posterior variance showcases the same thing, right? So we have three different metrics that allow us to say the same information with varying levels of, quantification off of that, or varying levels of uncertainty that's provided. So it's quite helpful for us to have these for all the different users, because some might be more driven to an underlying situation or an underlying metric. So with that, I'll wrap up my time here. And I'll just say that we have spent a good amount of time kind of building up PyBop to be an open source, fair, and free, collaboration. So we have quite a few different collaborators across the world at the moment, but we would be very interested to kind of expand that and work with the controls field even more, and think of areas that we could take the knowledge of both fields and really intertwine them well. So again, thanks to all the collaborators for this work. And if you're interested, we have a manuscript and examples and docs, and it can be easily installed via pip. So thank you very much.
Thank you, Brady. We might have, oh, I didn't know PyBop did design optimization there. I knew, but that's quite cool. I was going to ask about the cost function, or even that design optimization. Is there a way to impose constraints on sort of manufacturability? So like, can you actually manufacture that? If you want a DS of 10 to the minus 16, can you do that? Another one is, can you have a cost which is, say, like a drive cycle over the lifespan, instead of just sort of energy density, optimizing the life over the whole lifespan of it? How would you, is there ideas to do that, or?
Yeah, for sure. So both the answers to your question are yes. The answer to both questions is yes. The first one, I guess there's a couple ways of doing that. We can provide bounds on the optimization or the optimizing rhythm itself. That's one such way to provide a constraint on a parameter. The other one is we can, depending on the dynamics in the system, some of the parameters are constrained to relations anyway. So things like porosity and the active material volume fraction they have a linked representation of the dynamics are quite clear. Inside of the parameter set, we can actually encode that into the parameter set. So we can say that as we're, if we want to optimize the active material volume fraction, the Proxy is going to change in a similar approach for every value that we select. So we can provide a constraint that way. But yeah, the optimizers themselves provide us with a few different constraint methods. Like one of the things we support is SciPy minimize, which has a constraint-based method kind of baked into it. So we do have some examples showcasing how that would work. And then on the cost side, so the cost and the model operating conditions are kind of completely decoupled. So we can have any sort of drive cycle or dynamics in the system, or like any sort of operating conditions, and then provide a cost on top of that. So it is quite easy for us to have a identification process where we identify a parameter from a certain excitation and then a validation with a completely different one, but with this kind of like the same cost functions attached. So you could, have maximum likelihood, or with some Gaussian likelihood function for identification, and then you could do a validation with a completely different, metric or design optimization as well. Yeah.
Well, thank you. So I know I've held the questions here, but in the interest of time, I think we should kind of plow on ahead. So if anyone wants to reach out, I think PyBop it's probably going to become the benchmark for parameterizing these electrochemical models. So if anyone works with these models, go talk to Brady and co, and Noel and Volkan, everyone over there. So thank you, Brady. Noel, are you perfect? Okay. Do you want to share your slides, Noel? Should be the big square with the arrow. Perfect. I can see you now.
Yep. All right.
The floor is yours. Well.
Okay. Thanks, Ross, for inviting me. So I am Noel. I'm a postdoc at the control group at the University of Oxford, working with Professor Stephen Duncan. So same supervisor as Ross had in the past. And if we think about control for lithium-ion batteries, maybe one of the first things we think about is fast charging. So when you are traveling long distance with an electric vehicle, and you need to recharge in the middle, for instance, driving to the south of France, you want to be able to charge your battery as fast as possible. But if you would put a very high current through a battery, this wouldn't work, because as Volkan has spoken about, batteries degrade. So at the start of the lifetime of a battery, you start at a state of health of 100%. And over time, this state of health is decreasing. And how this state of health decreases depends heavily on how you use the battery. and so also on how you charge the battery. So that's why many companies are looking at fast charging, where they try to charge a battery as fast as possible, but limiting degradation. So one way to do this is first to apply a high current, the highest current you can, Imax, until a certain constraint is hit that may cause degradation, for instance, overpotentials that become too high, something like that. And then eventually when you hit some output constraints, for instance, the maximum voltage, then also you would limit the current signal. So if you want to be able to optimize such a charging profile for a battery, well, where we need to start is to have a model for a battery. And many companies are now looking into physics-based models to design fast charging profiles. So if you look at the battery, basically what is happening is that lithium ions move from one electrode to the other. You have this rocking chair mechanism, and there exist mathematical equations to describe how these lithium ions move. So for instance, you have diffusion within the particles, which you can model with PDEs. There is diffusion within the electrolytes, charge transfer kinetics, and you can put all these equations together, and then you get a physics-based model. And so for a control audience, what is important to understand here is that these models are distributed models. They depend on space and time, and they're also nonlinear and parameter varying. So these are quite complicated models, but eventually they give you an expression for the voltage as an operator on the current. And so for a given current signal, you can simulate the voltage, for instance, using PyBop, which is open source software developed at the Mathematical Institute here at the University of Oxford. And you can also simulate all the internal signals of the battery. But, well, if you want to use such a model for a specific battery, you first need to parameterize the model. And physics-based models typically have many parameters. So for instance, here the single particle model with electrolyte has 26 parameters. And many people look at estimating these parameters from time domain data, as Brady has mostly discussed in his PyBop presentation. But it's also interesting to look at frequency domain data. And that can be done by measuring the impedance of the battery. So here also for a control audience, I think most of you know how to measure impedance. So you drive the battery to a steady state, and then we apply small amplitudes perturbations in the current, sinusoids, and we measure the voltage response and estimate the impedance from those. And here we actually measure impedance over a very wide frequency range. So we start at 200 Hertz, that's the highest frequency, and we go as low as 400 microhertz. So these are very long experiments. And a battery is also typically nonlinear at low frequency, so it's also very important to check the conditions of linearity and stationarity. Now, can measure such impedance data at different state of charge levels. And here I represent the impedance in a Nyquist chart. Material scientists like to look, or battery people like to look at Nyquist plots of the impedance. It's actually an inverted Nyquist plot. And the goal now is to estimate the model parameters by minimizing the sum of squares between measured impedance data, Zn, and then the impedance of the model. But here, well, you need to compute the impedance of the model. And doing this for complicated physics-based models like the SPME, doing this analytically becomes prohibitively hard. So that's why we have developed also open source software within PyBop and PyBop, with whom we can compute the impedance of a physics-based model numerically. So how do we do this? Can take your physics-based model, any physics-based model you want, and we then discretize the model in space. So we get a certain grids over the spatial properties of the battery. And then this entire physics-based model can actually be rewritten in a nonlinear system of discrete algebraic equations. So you may have preferred to see here a nonlinear state space model, but in the work we did, we used here nonlinear DAE. So we have a mass matrix M, which is typically not full rank. And then we have here a very long state vector X, which contains all the variables on the, for instance, concentrations and overpotentials in the model on the different bounds of these discretized mesh. And then you have a nonlinear function f theta of the states, and then plus b, a column vector times their inputs. And this is the equation that PyBop solves to simulate a model. So now to obtain the impedance from this, that's not very complicated. We first linearize this equation around the set bounds. And so then we have small perturbations of the state, that's this x tilde. And we linearize a nonlinear function f, and then we obtain its Jacobian here. And the advantage of looking at PyBop is that you get this Jacobian using automatic differentiation. So we get an exact representation of the Jacobian. Then we transform this equation into the frequency domain. The time derivative becomes a j omega. And then we solve this for x. And there we have to invert a large square matrix, which would be full rank, as a Jacobian is typically full rank. And then you can get the impedance by dividing the state vector at the index of the voltage by the current spectrum. So for control people, these equations are really nothing new, but implemented in PyBop under PyBop ES, this allows to compute the impedance of any PyBop model at any operating point. And I think this is quite powerful, because doing this analytically is impossible. So if we, for instance, look at the impedance of the single particle model with electrolytes, in a Nyquist chart, you see different features in the impedance, and you see these features even better here in this dotted line, in the case where all the physical processes are perfectly separated. So there you can see that you have a feature for the series resistance, then semicircles for charge transfer kinetics, a certain shape for electrolyte diffusion, and a certain shape for particle diffusion. And so these, in reality, these physical processes overlap, their timescales overlap, but still looking at frequency domain data allows to have some separation in your data to estimate the parameters of these physical processes. So now let's see how we can estimate the parameters. And we will first do this in simulation. So we have simulated impedance data at 9 different state of charge levels from the SPME model. So here we know exactly which model has generated the data, and we also know the true parameters. And then we'll see if we can retrieve these true parameters by minimizing here this cost function between simulated impedance data and the impedance of the model. We allow the parameters to vary within quite large bounds here. And we have 18 parameters to estimate, and we do this with PyBop. So we try to estimate the 18 parameters all at once. So we have an 18-dimensional search space, and we allow 1,000 iterations of particle swarm optimization. And here we can get quite good fits, actually, relative errors under 2%. And the estimated parameters are actually also very close to the true ones. So this is good news. The parameters that are related to the large features in the frequency domain data are estimated quite accurately. But now we go to the real world, where we try to fit measured impedance data. We have measured impedance data on a commercial LG battery. And here, when we try to fit this data with an SPME model, we see that the relative errors are way higher, even until 25%, especially at the low frequencies. And this means that these commonly used physics-based models may not be sufficient to fit real-life impedance data accurately. So we need to give more flexibility to the model, for instance, allowing certain parameters to be functions of concentration, for instance, or adding different features. And the advantage here of this numerical impedance computation is that we can easily add features to the PyBop model and still compute the impedance, and then still use it for parameter estimation using PyBop. So let me then conclude. I will conclude in 4 points. So one way to do battery fast charging is to have a parameterized model, and then to design the fast charging profile from this model by constraining certain variables. And so to parameterize a model, impedance data is quite a useful source of data because you get this separation of physical processes that happen at very distinct timescales. And then we have made this open source software called Boem, which allows to numerically compute the impedance of any model that you implement in Boem at any operating point. And then finally, we try to estimate the parameters of the model using PyBop. This works very well in simulations, but on measured data, this is more complicated. So to end, I still want to thank my collaborators. So there are some people from the engineering department at the University of Oxford, but then also some mathematicians that helped a lot, and also Rob from Ironworks. So now I will be happy to take any questions.
Thank you. Does anyone have any burning questions for Noel? So either just raise your hand or in the chat. Because I could ask one, which is, so the errors seem to be in the low frequency tail.
Yeah.
Is that because it's an SPM? As in, is it because of the particle diffusion you have to do on multiple particles, or a high enough discretization, or I don't know.
So yeah, so when you try to fit measured impedance data, the error is indeed highest at the low frequency. So that's in the diffusion tail. So we think, yeah, the impedance we compute from the model is correct. So this, when you use enough discretization bounds, then you can model these, well, the analytical diffusion tails quite accurately. But actually the other important thing about the diffusion tail is that's dependent on the open circuit potentials, or on the slope of the open circuit potential. So here we use open circuit potential data. And if that data is not accurate enough, then well, the impedance will never be fitted well. Yeah. So that's a big downside. Well, that's a part of these physics-based models. Maybe 90% of these models are open circuit potential. And if you don't get that right, then your model is not very accurate. And then another thing is that we considered a constant diffusivity parameters. And these diffusivity parameters may have to become functions of concentration, which will allow more freedom to fit these diffusion tails.
Yeah. All right. No, I could actually bet 10 more questions, but they'll all be rubbish as well. They'll all be.
Oh, you can add them afterwards.
Yeah, afterwards maybe. That's really good. It's good to see what you've been up to. Could we now shift to Yuanbo?
Yeah, thanks.
Oh, thank you. I'll see you soon in Oxford, I'm sure. So yeah, so this is Yuanbo's battery zoo. So there we go. So I think this is some ideas that we've been cooking up, which kind of emerged, I think, from Dave's lab in some sense as well. But Yuanbo's really taken this forward and done a really good job of this. So Yuanbo, the floor is yours.
Thanks, Rose. Yeah, very happy to meet everyone, our experts in the field. My name is Yuanbo, and I'm a lecturer here in the University of Sheffield. I must start by admitting that I have zero background in battery, right? So my own research is in aerospace engineering and dynamic optimization. But you know what happens by having the office next to Ross. So I'm very happy here to present Battery Zoo, our parameter library for control and estimation of lithium-ion batteries, right? So this is a side project that joint work with Ross, Pablo, as well as our PhD student, Pan and Nicholas. So I will start by giving you a bit of motivation why, a library for control of batteries. So we know that control has been an enabler in many engineering fields, right? So in particular, for example, aerospace engineering, If you look at the physical system, the three axis of control system, is really there from the very early stage of aviation, right? But it's only that with feedback control that as one of the leading factors that brings air travel to the masses. A similar story with batteries, for example, just limit ourselves to smartphones. Then from the start of the smartphone age to now, the chemistries are still roughly the same, but we have far less low battery anxiety now, thanks to not only the larger battery, but battery management system with feedback control. So for example, we can bump up the battery charge very quickly in a matter of minutes. However, for more complex systems like electric vehicles or aircraft, we need something that is more advanced. And this more advanced drive for control algorithm is also somewhat fueled by the slow advancement in chemistry, right? So although the battery costs are decreasing rapidly, it's still very expensive to develop and scale up new chemistry. So what we use now are still really from the mid-2000s. And with feedback control, we want to make max use of what we have, right, to make it more efficient. And this drive for efficiency is even more significant towards battery packs, right? So we lose almost half of the energy density by going from cell level to packs. And this has largely also driven by the non-uniformity of battery cells, even if they come from the same production bench, right? We show in the figure on the right. And in the current pack designs, a lot of times the performance are dominated by the word cell. Therefore, by using smart control algorithm, we might have a lot of benefit that we can get from. In engineering system that integrates battery, because of the very big reduction in energy density compared with other traditional energy sources, there is an increasing need or stronger need in terms of optimizing its operation, right? If you just think at electric aircraft or hybrid electric aircraft that make use of battery, then there's very big need in order to achieve sort of the design range that we jointly optimize the operation of the energy and propulsion subsystem together with how we fly the aircraft in terms of flight trajectories. And in such a case, it's still not enough, right? So in many engineering problems, we have to even go one level up to look at engineering co-design problems where we co-design the physical system together with their operational profiles in order to strive for the maximum benefits. And in these large-scale design and optimal control problems, it requires computation light, but yet sufficiently accurate dynamic models. And this is where we see a quite extensive need of a battery library in order for us to do tasks such as optimal selection of cells and all optimal design of packs for example, together with the operation profile of an electric aircraft. And with that, I would like to present you the battery zoo, right? So we just made a preliminary release on GitHub, which contains roughly around 40 commercially available and experimental cells as of now. They're all based on different chemistries, what we might be able to infer from the OCV curves shown on the right. But they're all equivalent circuit models, which are suitable for the type of the large-scale optimization problem that we have in mind. To better facilitate the development as well as the use of this model library, which we call the Zoom, we also interfaced with, for example, the dynamic optimization toolbox, iClocks2, to create actual functionalities. One of the examples would be the field biologist, which is there to help to translate the battery data that are in the wild into parameters of models that can be used later. And also to facilitate the use of such a library, we also create an optimal control module where we call the zookeepers that can help us to come up with the optimal operation profile for battery cells, packs, as well as the engineering systems such as aircraft and vehicles. Lastly, we also create a PyBop interface, which we can not only contribute, but also benefit from a larger wide range of battery community. And next, I will just give you a bit of a sort of overview in terms of some of these additional functionalities as add-on modules. So with Zookeeper, we have an optimal control interface that can handle quite a wide range of problem formulations. So we have created one example implementation where we look at the optimal fast charging of battery cells subject to a number of different constraints. And here I give you sort of provided one example solution where I look at the sub-selection of cells. What we can see here is starting from the maximum charging rate of 5C, most cells already see a reduction very early on in the charging profile, and that is as they start to meet or quite strengthened in this particular case of maximum output voltage of 4.7 volts. Later down the line, you can also see the profile has been also been interrupted by other conditions, and these are the activation of constraints of RC voltage as well as the battery temperature. And we want to use this to demonstrate really how the cells are different and the optimal output profiles are different. So there's a lot of value in doing this optimization by taking the optimal choice of cells as well as optimizing their operations. Next, I'm going to the estimation module, which is what we call the field biologist. We've created this really for the purpose of supporting, making contribution to the battery library in a much easier manner, right? So this is a quite, again, flexible estimation framework. For example, can handle all different estimation problems, including state estimation, parameter estimation, as well as joint estimation of state and model parameters. What another functionality we have built into the field biologist is the capability to simultaneously estimate from multiple experiments and multiple segments of a single experiment, which we found very handy in our experience. And I will go slightly more in details into that. But we'll start with a simple estimation problem where we have some available data, right, that tell us what the OCV curve is, and we want to change that measurement. We want to change that to the curve. So in Battery Zoo, we support both global and piecewise polynomial fitting, and we not only try to make the fitted solution match the point, but also we focus on properties such as monotonicity of the fitted function so that it better correlates to the physics. Next, we're going to look at slightly more challenging problem, and that is the joint state and parameter estimation problem. And for this, we look at an example where we have 4 independent experiment data for a cell discharging from 4 at different amps. And what we have collected is actually a time series data regarding the output voltage against time. There are other parameters we also know, that is the weight of the battery, as well as the dimension of the battery, as well as the cell capacity Q. However, we do not make use of this cell capacity explicitly in the estimation problem because we want to serve this as a sanity check in the end. The items we will need to estimate are the state trajectories of the state of charge SOC, the RC voltage VRC, as well as the temperature, as well as static parameters. And these are for example, the coefficient for the degree 6 polynomial to describe the OCV, the Q, the series resistance R0, as well as the RC pair R1 and C1. And we want to do the estimation problem while still subject to a number of constraints regarding the bounds on the SOC, the temperature, as well as the monotonicity of the OCV curve. So from the definition of the OCV, an expert like Ross would tell me that, estimating based on an experiment that has the smallest discharge current might be the best choice, right? Most suitable choice. In this particular case, this is the data where we have for discharge at 0.6 amp. So if we run this dynamic optimization to generate this, we see a very good match between the measurement and the model output. At the same time, we also obtain the state trajectories as well as our estimated OCV curve. And by just general observation, there's nothing particular that would tell there's something that is of worry. However, when we apply the model with a higher current and compare the model output of the high current experiment, we see an increasing mismatch, especially for the 20 amp case. Now, what this tells us is the system identification using a single experiment can lead to large discrepancies because of the identifiability issue that has been mentioned earlier, and that will lead to large discrepancies in other operation conditions. So what we have equipped the field biologist with is ability to solve a single estimation problem based on all the experiments. And from this case, we see a much improved fitting in all different cases of different discharge currents. However, we still observe some sort of discrepancies at the 20 amp point. And based on literature and advice from Ross, what we have decided to improve the structure of the R0 modeling, right? So instead of modeling R0 as a fixed parameter, we made it a function that is second order with respect to SOC and first order with respect to the current. And overall, we obtain a quite good fitting in all different discharge current cases. And with that, we can have a look at the obtained OCV curve as well as the other estimated parameters. And now we also have a profile of R0 that is having a first order relationship with the current, as well as second order relationship with the state of charge. And next, we can do our sanity check, right? So we know that the capacity from the data sheet is around 3.120 amp hours. And we can compare that with what we have obtained from our estimation results. So what we can say is this multi-experiment setup provides a very good estimation for problems that may have identifiability issues, right? So beyond multi-experiment estimation, we also look at multi-segment estimation problems. And these are experimental data with duty cycles that are containing multiple segments. For example, in this VTOL duty cycle, there are different phases or segments that relate to the charging, including the post-charge resting, the takeoff, the cruise, the landing, and subsequent resting as well. Some of these phases are with very short time duration, but with very fast dynamics. So that means it's very interesting for identification problem. But some of them are with very long horizon and hardly things change, right? It's still fine to solve this problem as a single estimation problem. You should get reasonably good results. But what we have seen is that in the areas where we have very short duration of fast dynamics, our resolution may be insufficient when we try to still make the estimation problem very quick and efficient, right? Therefore, we have created this sort of multi-segment estimation setup, which we can tailor. We can break this sort of experiment into multiple segments and then tailor our resolution in each of the segments depending on the nature of the dynamics. And this also gives us additional opportunity to enforce additional midpoint constraints. For example, if the experiment in this case, we have obtained the information that before discharging, the battery had the SOC of at least 0.9, then we can actually enforce this constraint at this phase segment interfaces in order for our estimated solution to better satisfy these criteria. So in short, we have created a control-oriented sort of battery library in order to address some of the challenges that the current batteries are inefficient and no two batteries are the same. So some tailored solutions are often needed for actual engineering applications, such as electric vehicles and electric aircraft. So we call this the library battery zoo because it contains a wide range of electric parameters, and we have created additional functionalities, including zookeeper for control and field biologist for estimation. And then from the estimation results, we can also see there's quite substantial benefit we see in practice when we do multi-experiment and multi-segment estimation altogether. In the future, we want to further expand the battery library to contain more cells, as well as incorporate other model structures. We also plan to develop and release further extensions, for example, the VET for the battery zoo, in order to do estimation and control of aging mechanisms. And lastly, we want to provide some examples of co-design problems for this tool to push further up into the design chain to benefit the community. We want to make this, again, as an open source platform that everyone can contribute and benefit from, right? So if you have a data sheet or some experimental data, we're very happy to let our field biologists to archive and study it. And if you have co-design problems, we are very happy to let our zookeeper to do the control and the optimization of that. As of now, please feel free to contact us by email, and we'll try to plan a better workflow in terms of how to better engage with the community coming up very soon. So that's the end of my talk, and thanks a lot, and I'm happy to answer any of the questions you may have.
Thank you, Yuanbo. Again, if anyone has any questions, feel free to go in the chat or raise your hands. As you can see, it's very dangerous having an office beside me. We end up going a bit mad and talking about battery zoos and stuff. But yeah, I think it'd be nice to talk to Dave Howie's labs and see where PyBop and the battery zoo can. I think there's solving different problems, but looking at similar problems. So Thank you very much,
Great,
Yuanbo.
thank you.
Yeah, there's a lot to digest there, and yeah. For the final bit, we've overrun, but could I ask, is Adrien there?
Yeah, yes.
Hi, Adrien.
Yeah.
How are
Can you
you?
hear me all right? Good, thank you. Good.
So just to wrap up, I mean, we've heard a lot of kind of research about batteries and control, but it'd be nice to kind of hear from industry and see what's actually important and what's actually being used. And so thankfully for that, Adrien has kindly volunteered his time at the end of the day to help with that. And Adrien was one of the founders of BrillPower, which was a really good company. Which I would like to hear more about. So Adrien, could you just tell us what BrillPower is and kind of what's your technology and all that sort of stuff?
Yeah, sure. Thanks for inviting me. Great talks. Yeah, maybe just a bit about BrillPower. So, and we are a spin-out company coming out of David Owy's lab. So it's a battery intelligence lab, as it's called now, not at the time, but so we spun out in 2016 with 3 other co-founders, 2 of them also from David Owy's lab. And so basically what we do is what we call a battery intelligence platform. So basically we try to make battery better and perform better. There's 2 main aspects to the product. There's sort of the BMS plus power conversion. So that's like the hardware sort of side of things. And that basically allows us to charge and discharge battery modules and cells at different currents in the system. So in a big battery on the grid, we can actually control how much power each of these modules sees. So the aim basically is to extend the lifetime of these systems. So that we're not limited by the weakest link in the string of modules. So otherwise you have sort of a Christmas light effect where the sort of weakest module limits the entire system. Or you can reduce the oversize of your system because usually on day one, a battery maker tends to make it bigger. So as it degrades, it still perform after 10 years or something like that. So we can sort of reduce that oversize. So that's one aspect. That's sort of the hardware and BMS, which basically where we can control things more granularly. And then the other aspect is sort of the cloud infrastructure, which we call Brady Analytics, where we get data into the cloud from our systems. And there we can compute more advanced metrics and have algorithms for remaining useful for life, predictive maintenance, and these sort of things. And if I can maybe use a slightly abusive language, we use Brady Analytics to sort of close the feedback loop control with the hardware. So basically we sort of upload the data to the cloud, update the models that are embedded in the system, and so feed that back to the BMS, the battery management system. So that's sort of BrillPower in a nutshell. We're based in Oxford still, a few dozens people. I think it changes all the time, with 30, 40-ish. And yeah, that's us.
Yeah, it's really cool. I mean, there's several engineers on this call. So what sort of skills did BrillPower always sort of need from control, or not just control engineers, but people working in this sort of space? So what sort of skills do you think we need to push more? And
yeah, I think we do have controls engineer because we do state of charge, state of health estimation embedded on the system. So your classic Kalman filters, whether it's extended, unscented, maybe particle one day, but so that's kind of where we're looking at. A lot of data scientists as well. We work a lot in the cloud, so with Python programming for cloud computing. So like that could be machine learning, but we actually don't do that much machine learning. It's mainly sort of analysis and models, sort of like differential equations and so on. Anything Bayesian and so. And I think what skill we are looking for is like sort of the deep PhD level skills, but also the software engineering skill, which sometimes coming out of a PhD you don't always have. But yeah, that's kind of
yeah. I'm going to tell all my third year. I teach a third year control course, and we teach Kalman filters there. So I'm going to say, this is good stuff.
perfect. Still used.
Yeah. And what kind of, like the big research, where would you like the research community to go? I mean, if Brill was to say, okay, there's one problem, if there was good research working on there, where would you kind of recommend us to go look for and try and solve?
Yeah, I mean, I thought I'd maybe take a slide mentioning a few trends in the industry, so battery storage, like on the grid industry, and maybe that will trigger some thought on what could be research project there. I think the first one, which you're probably aware of, is the move to LFP cells generally. In stationary storage, that's pretty much 100% of the systems are LFP cells. The Chinese industry is sort of like driving the cost down and so on, and so being very effective at making very cheap LFP cells. Not that they're not good, but they are very cheap. So everyone's going there. So I think the flat OCV versus state of charge curve is a problem. And it's not just for state of charge estimation, then it's state of health, capacity spread, because you don't know which cell is where. And so I don't think you will get better sensors. So the question is, are there better algorithms that you can think of, I think, in terms of like filtering and sensor fusion or whatever it is to try to overcome that? I think another related trend in the industry is going to larger and larger format, like cell format. So currently we're at about 300 amperes, which is a big brick of cell. That's like the standard. But nowadays everyone's talking about 600 amperes or even 1000 amperes. So these are massive, massive cells. Yeah. So I think that bring a lot of challenges to the industry in terms of sort of spread in capacity across cells, because you don't have these parallel groups that sort of cell balance. And also thermal gradients are bigger. It's very hard to cool these cells. So I think you'll see more spread in degradation. But I think there is tools like ourselves at Brill, you can control more granularly, whether it's at the module level or at the rack level. But then it's the question is, how do you control, like how do you get metrics that are accurate enough to control based on, and what do you try to control? And maybe one last challenge which you alluded to is lifetime sort of control and estimation. I think it's moving so fast that by the time you have fully characterized a cell, it's already obsolete. So it's slightly contrarian view, but I think the business of cell characterization over a lifetime is just not gonna work. So how can you use operational data to sort of estimate all of this state of charge and state of health over 5, 10, 20 years? And I think in the industry, it hasn't been a problem yet, because people, it's just starting to be a problem, because people start seeing 5 years old battery and start seeing the issues of state of charge being completely inaccurate, and so on, and spread and so on. So, and maybe just to just finish off an opportunity, you mentioned more computational power. I think there's a scope there. Like, BMSs have very limited computational power, but now we can see edge computing. You can have a very small industrial computer located with the battery. So that gives you access to storage and computation. So you can think of like algorithm that has memory. So it's a recursive, so Kalman filter limitation is lifted. So what can you do with that? And I'm not saying machine learning everywhere, but I think you can do much more stuff.
Yeah.
Opens a lot of possibility.
Yeah. I'm so shocked. So I'm 600 ampere cells. I mean, that's I'm so that's massive. That's
yeah, okay. It's about this size.
Okay. And a lot of what we've been talking about is data, and sort of batteries need data to make smart decisions. And I've always found that, especially in research, we don't have the data needed to make the smart decisions, really. Is that a problem for BrillPower, or do you just crank out loads of experiments and I don't know, or how do you find that problem?
Yeah, I think data access is definitely a big problem in the industry. It's very closed up, so it's really hard to get battery data for a very big system. That's something we struggle with. So we still rely on academic data quite a lot, like academic data sets, which are not always quite representative of the real life. But definitely problems there, and I think that's somewhere industry could improve to help academia and vice versa.
Yeah, I remember a couple of papers a couple of years back about that, and I haven't heard anything since. So yeah, yeah. I mean, so can you tell me a bit about like the startup journey? I mean, I know it's been stressful, but like how is it like? How would you encourage people to form a startup, and how would you encourage them to go about it? And is there support? And I'm not sure about that.
Yeah, I mean, I know the Oxford ecosystem more than anywhere else probably, but I mean, I would encourage people to try it. Definitely, it's not it's definitely fulfilling and interesting. It's also hard to find the co-founders to do it with, because you need the co-founder to help. I mean, fundraising, for instance, is not the funniest part when you are a technical person. So I think finding the right co-founders definitely helps. In terms of support, usually universities have different levels of like accelerators and competitions and so on. So that's where I would start. Just be very greedy with your company shares in the beginning. That's what I would say. It's just like try to find free money at the very beginning, because later on it becomes harder and harder. So.
Okay, because yeah, I think I don't know how much, if I was to do a spin out today, I don't know how much the university would take, but I think it would be quite a lot, really. And then that's yeah. Anyway.
It could be quite a lot, yeah. But it's negotiable. Everything is negotiable.
Okay. Yeah, and is there anything you would have done differently? So, or how, when you first started, did you have to pivot or change, or?
So initially, we focused on sort of reusing second life batteries for sort of helping the developing world, which was a very sort of beautiful mission. We had to pivot away from that for two reasons. The first one is that second life cells are very difficult to sort of reintegrate into a pack. And then eventually the cost of new cells came down. So that made it actually not really feasible. And the other thing is the market of like developing world has very little money to offer. So if we had a premium product for markets that can't afford it, that just didn't add up. So we had to pivot to something different. Eventually, once the costs come down, they will come back to it. But if I do something differently, I would say hire a good software engineer very early on, because that can be quite transformative.
Yeah.
I think the power you get from like data science and controls engineer with someone who knows software very well can really boost how fast you develop things.
And just another thought. I mean, a lot of BrillPower's technology improves the lifespan of a battery. So to convince people, like, you save them money by making their battery last longer, or was that hard to convince people that at the start you need to have our stuff, because in 10 years' time you're going to be earning more money?
That's echoing to the first talk of this second session about sort of amortization and sort of cost over time. And that's why when I explain it, I say increase lifetime, but you can also reduce oversizing. And we had to pivot quite often to reduce oversizing, because that's a reduction in cost today. Whereas reduction in cost in 10 years' time, usually people are less inclined.
Yeah.
So we had to rephrase this sort of messaging.
And so a question from Nicolesh. So did you see your research career with eventual commercialization in mind?
Oh, very interesting question. Not really. I think it was all a very happy accident. I think I mean, the story is that we wanted to combine the three of the co-founders wanted to combine our research into a project, so we could go to a conference together with different aspects of research. I was more state of charge, and Christoph was more degradation, and Damien was more electronics. So we sort of tried to think of a project that would make sense all together, so we could go to a conference. And that's how it was born. And then we did a competition, and it just snowballed from there. But from my point of view, there's no particular conscious academic research kind of conscious effort to commercialize. But I would definitely encourage everyone to do that. Not, however, because I think that makes your sort of research much more applicable and valuable.
Was that a conference? I can imagine it in good stuff.
California.
Oh, California. Okay. Yeah. Okay. Fair enough. Yeah. All right. So if what are your thoughts on? There's a balance, I think, between exploiting the current chemistries and current cells and looking towards the future. So solid state is always meant to be around the corner, and all these others. What are your opinions on? Is there still scope to maximize the current technology, or should we be looking towards there's this wave of solid state or whatever that's coming that we should pivot towards as well?
I think especially on the energy storage on the grid, LFP will be there for a while before it gets replaced. I'm not an expert in materials, but yeah, solid state's always around the corner. It seems like I think it's Mercedes eventually has a car with it with some solid state, some form of solid state. Coming soon, as usual. But I wouldn't say don't focus, especially in academia, you want to focus further ahead, definitely. But I think there is scope to like spend a bit more focus on especially system level. Like there's a lot of like research on cell level, so state of charge models and so on. But then how do you scale that up to thousands of cells a series in a system? You know, the brute force approach of running 1,000 Kalman filter, it technically works, but you know, it's can we do better? Is there ways to like make algorithms that can accommodate these sort of large scale systems? I think that's an interesting topic, for instance, that is always overshadowed by cells, cell level and cell material, so research.
So just on, I mean, how much compute is typically available for an online BMS? I mean, is it an Arduino or is it something a bit more junky?
So I think the electronics, the BMS itself is like a microcontroller. So like if you're lucky, you get an STM32 or something like that. You might get floating point arithmetics for 32 bits. I think at the edge, you can have sort of an industrial computer, which should be sort of a beefy Raspberry Pi or something like that, the equivalent. And that's where you can have some storage and some computation there. So I think that's an interesting sort of development, which you see in the industry. You start seeing battery analytics companies that they put the device within the container. To enhance the local battery and sort of compute better metrics.
Yeah. Oh, I don't know. That's really useful. I think I've learned a lot, Adrien. Does anyone else have any questions for Adrien? If not, I'm conscious that we've overrun by 10 minutes. And again, Adrien, I owe you a drink now. Next time.
Yeah. Next time you're in Oxford. Yeah.
Yeah. I appreciate you and all the other speakers and all the in the audience attending. I had a great time. But I think with that, I think we can close the session. So yeah, thank you all. Thank you, Adrien. Thank you, everyone. And I'll see you all soon. Yeah, bye.
Thanks, Ross.
Thank you for organizing it.
Thank you for organizing it, Ross.
Cheers, that was brilliant.
Thank you. Bye-bye.
Thank you so
Thank
much.
you. Bye-bye.